Susumu. He is the first speaker. Okay, so good morning, everybody. I think we can start the session. So the first session for today of the High Energy Focus meeting. We continue on science-related topics. So today, this morning, we have AGN, gamma ray burst, and synergies, multi-messenger and multi-wavelength synergy, plus two contributed talk. So the first speaker of today is Susumu. Here we go. No, this is not the right talk. He will be talking about gamma ray burst. Now, I don't know exactly the title because no. Do you need help? Yeah. Ivano Marcus, would you be ready to start? Okay, so I propose that we switch the order of the talks because there is a hiccup, a technical hiccup with the slides. So we start with Marcus Botcher, and we talk about AGN. So can so we start with Marcus, and then we, in the meanwhile, they find your slides, Susumu. Hopefully. Did they find it? El chaos. Okay, so yes, you can talk from here, or if you prefer the ice cream, I give you the ice cream. The remote? Here we go. So please, Marcus, when you want.
All right, thank you very much. So yeah, everything there is to know about AGN in 20 minutes is probably not an easy task. So I'd rather focus on radio galaxies, in particular AGN that are not blazars, which are the most commonly detected gamma ray AGN. So maybe just as a quick introduction on AGN, so that at least I mention all classes of AGN. I'm not going to go through all of this. So there's a lot of classes of radio quiet AGN that do not have a jet. But the classes of AGN that we typically see in gamma rays, in particular in very high energy gamma rays, are the ones that are actually jet dominated. So if you look at the very high energy gamma ray all sky view, then everything of the galactic plane, almost everything of the galactic plane is actually active galaxies. And the vast majority of those that we see in very high energy gamma rays are blazars. That means radio loud AGN, where the jet is pointing right in our direction. Then there's a couple of radio galaxies. As it turns out, all of those are actually of the Fanarov-Rayleigh type 1 radio galaxies. Everything is AGN outside of our galaxy, with the exception of 2 starburst galaxies and a couple of gamma ray bursts. Again, everything else is radio loud AGN. So that means what we'll study with very high energy gamma ray instruments is these classes down here, either blazars where the jet points towards us, or radio galaxies where the jet points away from us. And in particular, from the radio galaxies that we see side on, essentially, it's the class 1, the Fanarov-Rayleigh class 1. Maybe for the younger ones in the audience, the Fanarov in the Fanarov-Rayleigh classification is the Bernie Fanarov that gave the invited discourse last week. So the class 1, where the radio emission is dominated near the core and it fades out towards the radio lobes, whereas FR2 radio galaxies are very faint near the core and dominated by outer lobe emission. So now, typically, one models the emission of radio loud AGN, in particular blazars, but in most cases also the radio galaxies, with leptonic or hadronic models. I will only mention the leptonic models here, where we have a relativistic population of electrons that's accelerated by some mechanism like shock acceleration or magnetic reconnection or others, with radiative escape and cooling. And then these relativistic electrons produce synchrotron emission that dominates from the radio up to optical, ultraviolet, or X-rays. And the high energy emission is dominated by Compton scattering of the same electrons of lower energy target photon fields, like the synchrotron field, or external target photon fields. So now we see mostly blazars in very high energy gamma rays, because in that case, we have relativistic effects like Doppler boosting that enhances the luminosity. So the apparent luminosity that we see is actually a Doppler factor to the 4th power times the intrinsic luminosity. These Doppler factors are of the order of the bulk Lorentz factor. That's of the order 10 or 20 or so. That means we see them actually some 10,000, 100,000 times brighter than they actually are intrinsically. And that, of course, helps with their detection in gamma rays. And also, we see short-term variability because the intrinsic variability is shortened by 1 Doppler factor in our observing frame. So now there really is only a handful of radio galaxies detected. That's the whole list of them. We'll not go in detail through all of them, but what stands out is that really all of these are either the FR1 type radio galaxies, that means the core dominated radio galaxies, or they have an uncertain classification. So that means possibly the rapid deceleration of the jet flow within the first few parsecs, or maybe a kiloparsec, might actually help convert kinetic energy of the jet into internal motion, into relativistic particle acceleration, and that helps us to see them even off axis. So let's go through a few special examples. So there's maybe the most famous one, Centaurus A, is the closest AGN to Earth at only about 3.8 megaparsec. And this is the only extragalactic source that is actually spatially resolved in gamma rays, so both by Fermi-Lat and by Hess. All other AGN that we see in gamma rays really just appear as point sources. So this is the Hess result in particular. So at the beginning, I should probably apologize that my talk will be very much Hess biased. First of all, because we have Hess pretty much next door here, and because I'm a member of the Hess collaboration. And many of these radio galaxies are actually in the southern hemisphere, so they can in fact only be seen by Hess of the three major instruments, Hess, MAGIC, and Veritas. So Hess has in fact spatially resolved the emission from Centaurus A, when not really in a nice image, but at least there's a significant extension of the Hess emission along the jet direction with a major axis that corresponds to an extension of about 2.2 kiloparsec. And that clearly indicates that relativistic particle acceleration happens not only quite near the core, but actually on kiloparsec scales. In terms of spectrum, Hess has also discovered that in addition to the upturn of the spectrum in the Fermi-Lat, that actually connects nicely to the Hess spectrum here. So there's not just one single power law component. There's clear evidence that beyond the Fermi-Lat low energy power law, there's a second component sticking out. And in terms of modeling, it clearly requires a second radiation component, which isn't too surprising because in radio images, we see the jet consisting of multiple jet components. So it's not implausible that also the higher energy emission is composed of multiple components, at least two in this case. Another famous example, of course, is M87. That has been target of multi-wavelength campaigns, in particular recently with the Event Horizon telescope. We had a special session on EHD results last week, where some of this has already been shown. So this is a composite image of the 2017 campaign by the EHD multi-wavelength working group. So this is, again, one of the closest AGN at about 16.8 megaparsec. And there have been these multi-wavelength campaigns. The first one in 2017 that has already been published. The multi-wavelength campaign of 2018 has just been submitted for publication by the multi-wavelength working group. And there have been subsequent campaigns in later years as well. So maybe the major result from the 2018 campaign was that we observed a very high energy gamma ray flare. All three instruments, Hess, Veritas, and MAGIC, coordinated observations with EHD to have nice temporal coverage here. It's the first major gamma ray flare that has been seen since 2010. Put that in perspective, this is the long-term light curve here. Here we have the very high energy gamma ray light curve. You see the previous gamma ray flares that have been seen in 2005, 2008, and 2010. The 2005 actually, there was quite a bit of confusion of where the flare actually occurs and where the very high energy gamma ray actually originates, because it could either be very near the core or there's this bright spot HST1 that happened to undergo an X-ray flare resolved by Chandra around the time of this 2005 flare. So at that time, a lot of people have actually speculated that maybe the very high energy gamma rays are actually coming from this HST1 spot. But in the later flares, you can see that the HST1 spot really just fades back down. There's nothing happening. And in contrast, this is the X-ray emission from the core that consistently flares along with the very high energy gamma rays. And there's not a major flare, but also a flare again of the core region associated with this very high energy gamma ray flare. So it seems to be pretty clear now that the very high energy gamma ray emission really originates near the core region. Also from morphological studies with Hess, we have tried to find evidence for spatial extension of M87, did not find any, and could thereby constrain the extent of the very high energy emission to, well, 4.6 kiloparsec. That's not terribly constraining, but at least there's no evidence for particle acceleration on large scales. Another special case is IC310. This is finally one that's not by Hess, but this is seen by MAGIC. This was originally classified as a head-tail radio galaxy, so with the kind of bent radio jet structure, again, very close by. So MAGIC detected this above 300 GeV. And in particular, as I was saying, in blazars, the relativistic effects help us with the rapid variability by shortening all timescales. So this very rapid variability on sub-hour timescales is not something that one expects to see in a misaligned jet. So the speculation here is that maybe the inner jet is in fact not directed in the same direction as the outer jet. So there could be a bent jet structure, that we have a kiloparsec, a parsec scale jet structure that's more like a blazar, and the jet bends away from us on larger scales, so that we actually classify it as radio galaxies in radio images. One more example is Sparks 0625-354. That's again another Hess detection, very relatively nearby. But on the other hand, 220 megaparsec, I'll come to that in a minute, is in fact the most distant radio galaxy, the most distant non-blazar AGN that has been seen so far. But then again, on parsec scales, the jet in fact appears one-sided, as you see in blazars, where the jet pointing towards us is strongly Doppler enhanced, and we do not see the counter jet that's going in the opposite direction. So Hess has detected this, was first seen in 2012. So at that time, there was no significant variability seen. Coming back to the point here, comparing all the radio galaxies that have been seen at very high energy gamma rays, this is by far the most distant one. So again, probably indicating that we're seeing something that's closer to a blazar than a radio galaxy due to this small scale jet structure. Because non-beamed emissions, so if one tries to apply a regular blazar model, but off axis, it turns out to be pretty much impossible in terms of parameters required for this. So, as I said, initially, in the initial detections around 2012, there was no significant variability seen, but in later observations in 2018, there was actually variability in the sense that at the beginning of the observations, the source was in a flaring state with a rapid decay on about a 6-hour time scale. So again, it's not something that you expect in a misaligned jet, again, suggesting that possibly we see a blazar-like jet on small scales that bends away so that on larger scales, it's characterized as a radio galaxy. One final example of an AGN that may have been detected that is not a radio galaxy. It's a very special case. So this is NGC 4278. So that's just an elliptical galaxy relatively nearby, similar distance to M87. That's a low luminosity, so liner type AGN with a very weak radio jet, very much subdominant, very low Eddington ratio here. So it's a very ordinary, but barely an AGN, so to say. And obviously, nobody in their right mind would have had the idea to point Hess or any other Cherenkov telescope to this galaxy. Nobody would expect to see very high energy gamma rays from an AGN like this. But LASO has actually seen a gamma ray source. You can see the spatial coincidence right here. It is by far the best candidate of the counterpart of this LASO source. There have in fact been 2 other AGN nearby, but a spectral comparison of the Fermi-Lat spectrum and the overall broadband SED and the LASO spectrum really just made no sense. So this seems to be the only plausible counterpart here. Most notably, there's also evidence for about month timescale variability. It's clearly not a steady source. So that again is something that might hint at an AGN nature here. So one looks at the spectrum here, that compares it to other well-known, very high energy AGN, like Macquarie and 421, of course, one of the brightest here. The spectrum we see from NGC 4278, the black points, is not really remarkable. It's very much in line with what we see from other radio loud AGN. But in terms of luminosity, you see other gamma ray detected AGN here in terms of radio luminosity and very high energy gamma ray luminosity. You see in radio luminosity, it's way down compared to all other AGN. So it's really very much atypical. It's a very radio quiet, very faint AGN that nobody would have ever expected to see as a very high energy gamma ray source. So to summarize this, so far all VHE detected radio galaxies are either of Phaneroff-Rayleigh type 1 or uncertain type. Cen A, again, is the only spatially resolved gamma ray source outside of our Milky Way so far. Rapid, very high energy variability, and other evidence actually supports the picture of the jets in these radio galaxies actually being aligned on small scales and then bent away so that on larger scales they're still classified as radio galaxies. And there's that special case of NGC 4278. That's possibly, if this association really turns out to be the correct one, is the first AGN that's radio quiet with a very faint radio jet, low luminosity AGN that has been detected in very high energy gamma rays so far. And I think this is really where wide fields, very high energy surveys, like with SWGO and with LASO, can make great progress, because this is the kind of source that nobody would ever had the idea to point a telescope to. I think it's only in wide field surveys that discoveries like these will be made. Thank you.
So thank you for the nice talk. Before asking the audience, let me remind people remotely connected that they can raise their virtual hands, and I will keep track of them. So first question here, Ulysses.
Yes, thank you, Marcos, for the presentation. And yesterday we were talking, myself and Roberta, about how the beginning of the third generation of Cherenkov telescopes has MAGIC and Veritas has really somehow reignited the research in this field of AGN and relativistic jets with the discovery, for example, of ultra-fast variability. And now it's very interesting to see your last 2 points in the summary, that the wide field survey instruments are already picking up some very unexpected objects, which might restart a new small revolution also in our views of these sources. So this is a point that I would like to make. I think that's very interesting. But would you like to speculate a little bit more? I mean, do you have some ideas on storage of what could be reviewed? Is there any sources that you would expect to also be picked up by these survey instruments, or this is all very new?
I mean, the first thing that would come to mind would be sources like NGC 1068, right? That's the most significant ice cube AGN. Obviously, there's high energy particle acceleration going on there, so this might also show up in very high energy surveys. I mean, NGC 1068, of course, has not been seen in very high energy gamma rays, only by Fermi, but I could imagine that there may be other Seyfert galaxies that might show up.
Marcus, thank you. Nice review. Is IC310 accessible, imageable? You can image it in VLBI or with the HT, so you can look at the bench structure, jet structure.
I think so. I'm not sure exactly what its declination is right now, but I think it should be.
Yeah, because it's nearer than Macquarie 421,
okay.
501. Their imaging. Yeah, thank you.
Yeah, just to mention that in the AGN survey by Hawk, the one published in NEPJ, we had some evidence for the Veritas source, and then for one AGN very near the LASO source, 1ES 1215 to 303. And then in the revised version, which I showed in a poster in the AGN session, we have evidence for like 6 more at the 3 to 5 sigma level, of which a couple are not identified as TeV source. So it's a poster I put in the AGN symposium if you want to check it.
Oh, well, thanks.
Thank you. So this basically confirms the last point that he made. Okay, thank you very much. I would thank once more the speaker. And now we proceed with Professor Susumu Ivanov. He will be talking about gamma ray burst at very high energies and in the multi-wavelengths context.
Yeah, sorry for the problem. Good morning. Great thanks to the organizers for the invitation. It's my first time in South Africa. I'm still haven't seen much, but I hope to spend a couple more days. Okay. So I think the title, yeah, okay, thank you. In the title I submitted, I had multi-messenger implications, but for the interest of time, I'll keep that to a minimum and focus on gamma ray burst at very high energy. So in the beginning, after some introduction about key facts and questions, I'll cover some of the recent results on TV detections of GRBs, long GRB and a low luminosity GRB detected by HESS. And then I'll spend a fair amount of time in the boat GRB, which is, of course, the big news, and particularly emphasize, the evidence for structure jet and the seeming lack of prompt emission at TeV, which is probably the new results for this GRB and with future prospects. Okay, so what do we know and do not know about gamma ray bursts? So they are transient and cosmological distances, typically a redshift of 1 or above. There seem to come in two types: long soft and short hard. Long GRB are, at least some of them are known to arise from massive star core collapse events. Short GRBs, it's not as certain, but still there is good evidence that they arise from compact binary mergers. In either case, they end up with a compact object, which by mechanisms that are not totally understood, gives rise to an ultra-relativistic jet of bulk clearance factor of a few hundred or so. So the gamma ray burst itself, the emission seen in hard X-rays and MeV gamma rays with their regular time variability, the so-called prompt emission, is thought to arise somewhere within this ultra-relativistic jet. This jet eventually interacts with the ambient medium and produces this relativistic blast wave. This is thought to give rise to the afterglow, lasting on much longer time scales than the prompt emission. For most part, from radio to optical to X-ray, probably up to GeV, they're thought to be synchrotron emission from electrons accelerated there. The newly detected TeV emission is also, at least what we've seen so far, is part of the afterglow emission. And okay, sorry. Yeah, so this is the afterglow emission at radio, optical, and X-rays. Occasionally, we also see emission from the reverse shock. So this is also most likely synchrotron emission from the reverse shock and of this external shock that's seen in optical in radio, which is more short-lived, maybe 100 seconds to hours or so. So what we don't know, the nature of the central engine. Many people advocate a black hole, but there's still a sizable camp who advocate magnetars. Maybe both are important. So this is still an open question. How the ultra-relativist jets are produced. Early on, there was some suggestion that you could have deposit positrons through annihilation of neutrino antineutrinos in a baryon-free region. That's probably not so efficient. There have been a lot of discussion about MHD-driven jets, possibly also the Blandford-Ziniak process, where the energy of the rotational energy, the black hole extracted via magnetic fields. This is still an important open question. And then probably the biggest mystery is how the prompt emission is produced. We know it rises somewhere in the ultra-relativistic jets, but by what mechanism is uncertain for a while. There's been widely discussed mechanisms, internal shocks, where you have shocks due to inhomogeneities within the outflow. You can have synchrotron, electrons accelerated there in synchrotron emission, reaching MeV energies, but it's known to have some challenges, like particularly the efficiency. So very different mechanisms like magnetic reconnection is also being widely discussed. Could also be a photospheric emission. So these events are really highly superadditant. So at the base, it's very optically thick. So they could have quasi-thermal emission reaching these MEV bands, and that could also be a mechanism. So to summarize the key established facts, again, there are luminous transients at cosmological distances. They come in two types, long and short. Prompt emission somehow occurs within the collimated ultra-relativistic outflows. The best understood part of GRBs is the afterglow. We know it's probably due to an external shock, blast wave decelerating the ambient medium. For a large part, it's synchrotron, probably from radio up to GeV. TeV emission is probably something different, but I'll get to that. And long GRBs are triggered in massive star collapse, and short GRBs probably in compact binary mergers. At least, maybe it's not quite established yet. The one clear case, of course, is 170817, but that's a rather special type of GRB. So this is maybe not in quite established as the others, but it seems to be good evidence. The key open questions, so the nature of the central engine I mentioned, the jet formation mechanism, the prompt mechanism, and then there are probably other questions that are a bit more a higher order detail, I would say, but it's nevertheless interesting. So for the afterglow, the microphysics, how the magnetic fields are amplified in the external forward shock, I'll get to that. How the particle is accelerated, it's a shock, but it's ultra-relativistic. So in the shock rest frame, the particle distribution is highly anisotropic, and it's not easy to cross back and forth across the shock as in non-relativistic shocks. So this is still a bit of an open question. There are some peculiarities seen in the afterglow like this, which I won't really discuss, but in fair fraction, you see this shallow decay, so-called shallow decay and X-ray flares, which are known. Low luminosity GRBs, which could be a different class. I'll get to this later. And you could also maybe ask the question that how much do they contribute to ultra high energy cosmic rays and high energy neutrinos? Okay, just a bit of basics on the afterglow theory. I won't go into too much detail on this. So there's this decelerating blast wave, a relativistic version of a supernova remnant. Like a supernova remnant, initially you have a free expansion phase where the gamma bulk Lorentz factor is constant, but as it sweeps up enough mass in the external medium, starts to decelerate, enters a power law deceleration phase. Analogous to the set-off-Taylor phase in supernova remnants. It could be the decay index is different, whether it's the ambient medium is uniform, or it's something more like a stellar wind environment where it's dropping as r to the -2. There are various parameters, the initial kinetic energy, the external medium density. This determines the dynamics. The jet opening angles is also another parameter. Then there are these microphysical parameters, which are not understood in detail, so they're parameterized. The fraction of shock dissipated energy in magnetic fields, usually called epsilon B. Epsilon B, the same fraction accelerated electrons. The electron injection spectral index. There's also the fraction in number of swept up electrons that are injected into the acceleration process, which is different from the parameter in energy. So even in the simplest afterglow model, there are 7 free parameters, which are used to fit, which are constrained through fits to multivariate data. So the electron distribution will be injected with the power law energy, but then as it evolves, part of it can cool. If it cools above a certain energy, it's called slow cooling. In certain situations, it can be the case that even the lowest energy injected electrons cool, so that's called fast cooling. And these are all time evolving, so you can have a transition between fast cooling and slow cooling and so forth. And when you're looking at a specific energy band, these evolving spectra will generally be going the optical and seen about 1 day, from which we can deduce that the opening angle of the jets are something like 10 degrees or so, typically. Okay, so about going on to the recent TV detection of GRBs. There hasn't been a whole lot, but we have a handful, and interestingly, within the handful, there seems to be a fair amount of diversity. So there are 3 long GRBs, maybe 1 possibly short, although this one is not of high significance. Very interestingly, there are these low luminosity GRBs that have been detected, particularly the one by Hess. And also, we recently have this extremely high luminosity GRB, the boat GRB. And I'll just focus on these 3 events: the long GRB, the low luminosity GRB, and the boat GRB. So the first really high significant detection of a GRB was by MAGIC, this long GRB 190114C. So this is the multi-wavelength light curve comparing light curves at different energies. You see the prompt emission here, and then the transition to the afterglow around here. Fermi is seen around here, and the MAGIC detections are around here. And so you see that it's a very clean power law that seems to be following the X-rays and partly the GeV gamma rays. So what we detected with MAGIC seemed to be predominantly afterglow. The radiated power is compared to the X-ray and GeV energies, so it's not just like a minor additional component. And it seems to be correlated with the X-ray, so it's probably has a close relation with the electron synchrotron emission in the afterglow. And what we showed in one of the MAGIC papers is that it's very likely a component that is distinct from the synchrotron emission because it is significantly beyond the so-called synchrotron burn-off limit. Now, the synchrotron burn-off limit is the maximum synchrotron photon energy for electrons dominated by synchrotron cooling. So the argument goes like this: assume the acceleration time is proportional to the gyration time of the particles. So it's inversely proportional to the magnetic field. That's what you'd expect in the so-called Bohm limit, and that's what you want if you want the particles to reach the highest energies. The synchrotron cooling time is inversely proportional to the inverse square of the magnetic field. The maximum energy, electron energy, determined by where this is equal. So the maximum electron energy will be proportional to b to the minus 1/2. The synchrotron photons emitted by this maximum energy electrons will be b times the squared. So the magnetic field actually drops out, and it's just fundamental constants times the bulk Lorentz factor. Numerically, it's around 100 MeV times the bulk Lorentz factor. Now, the bulk Lorentz factor it depends on the model, but you don't really expect it to exceed values like 1,000. So once you get the TeV energies, it's very likely a significant beyond this limit. And this is what we showed here. As a function of the time, the energy of the photons detected by MAGIC, it's around here. And even for rather optimistic values of assuming the bulk Lorentz factor, the expected synchrotron burn-off limit is here, and we're significantly above this. So it's likely something different from synchrotron. Most promising is synchrotron self-compton from the same electrons. And this is important because it gives valuable new info on the physics of the conditions in the relativistic shocks and particle acceleration, since it's different from and has different dependencies on the magnetic field and so forth. There's been the suggestion that you might be able to evade the synchrotron burn-off limit if you consider inhomogeneous magnetic fields, but that's only going to give you an excess with a very much lower luminosity. So you still end up with 2 distinct spectral components. If you have more questions, please ask me about this later. Okay, so for low luminosity GRBs, they could be a different class from the classical long and short GRBs. Only a handful are known. And the important thing is that the basic nature of these objects they're not known. They could be maybe off-axis classical GRBs, so-called dirty fireballs with a much lower Lorentz factor than the classical GRBs, or it could be totally different nature, like shock breakout events. And the interesting thing is that when you estimate the luminosity function, and the integrated energetics of these objects, they could be actually more dominant over the high luminosity GRBs. So they are really interest for as potential sources of diffuse fluxes of high energy particles like ultra high energy cosmic rays or high energy neutrinos. And so interestingly, Hess detected this a low luminosity GRB 1908-29A. So then in the Hess paper tried to discuss, the main point of the paper was that the spectrum didn't seem to be consistent with sequential self-Compton and maybe more consistent with a single spectral component. But to me, that's not the most interesting point. The most interesting point is that it's coming from this low luminosity GRB whose physical origin is unknown. And possibly they could be related to the origin of diffuse neutrinos, ultra high energy cosmic rays. So the UTV detection could shed light on this problem. At least there's one work where it's tried to address the nature of this GRB and suggested that it may be a GRB with abnormally low prompt efficiency. We still don't know yet, but this is the I think the most interesting part about the low luminosity GRBs. We just don't know the basic origin. So having a new channel's observational window is very important. Okay, and I will skip these couple of slides on the multi-messenger thing for interested time and go to the boat GRB. So the boat GRB, you heard from how yesterday it's the brightest GRB on record. It might be a rare event, quite rare event. And what Lasso saw was this emission that is slowly rising and slowly decaying, and it doesn't seem to be correlated with the prompt emission. So it's probably afterglow. And the real key result is this. Lasso found, so this is the light curve and separated into different energy bands, and they are all very similar. So, and you also see that you see a peak, and you also see this break. And so this is what is achromatic. So it's independent of energy. And what's showing is that, so these breaks in the light curve is not some something to do with a spectral break, but rather is this part is probably a jet break, and this part is the onset of the afterglow, which I didn't really mention, but it's a reasonable interpretation. And what this shows is that from the light curve, so the jet break, which seems like a jet break, which occurred at a few thousand seconds, or sorry, a few hundred seconds, which is typically much shorter, shorter than what you typically see in like the optical. The jet opening angle is very narrow. It's less than 1 degree, so it's a very narrow jet. But this is also makes the prompt. So if the prompt emission was collimated within this angle, it makes the energetics in a reasonable range. So this is kind of self-consistent. But this is not the whole story. And so if you look at the multi-wavelength emission at later times, particularly the X-rays, it's the decay slopes are much shallower. And which indicates that you need something more than just a narrow inner jet, but the afterglow that is coming from what is a structured jet. So this outer parts of the jet with more, probably a bit lower energy and lower bulk clearance factor. And this is to some extent expected. Long GRBs arise from GRBs from massive stars, so they have to make it out of the star. When people simulate this, the propagation, you expect that there's a fast, narrow core, more energetic core, and a slower and less energetic wing. And this may be the first time we're seeing this in the afterglow. So it's important, and it would really, in principle, tell us something very important about this, the physics of jet formation and propagation. And okay, so there are a couple of structured jet afterglow models. Okay, so let me just say, so there are a few models that are apparently similar, but they provide a reasonable fit to the available data. And however, when you compare the actual parameters that are using what they claim are the best fits in each model, they're really significantly different. And especially even for the inner jet, actually, especially even more than the outer jet, the inner jet is very uncertain. So they're between like the external medium density that is assumed in two of the models is different by 4 orders of magnitude. And what you look at, when you actually look at the microphysical parameters, they also have significantly different values for the magnetic field. So it seems that the models are still very much unconstrained. And it's kind of not, it's in hindsight, it's not surprising because as I mentioned yesterday, the lasso data was very exquisite. You had high statistics, but there's very limited simultaneous observations and at earlier times. You only have a little bit of GeV and X-ray, no optical. So if you had early optical and more X-ray emission, you should be able to disentangle these models, but we don't have that yet. Just one last point. So it turns out that there is a little bit more data that has not been published yet on this GRB that might break actually some of the degeneracy. And that is the late time LST observations. And I can't show you the data yet, but we have some data here, and which will be presented in the upcoming conferences soon at TEPA and Gamma. And I can say that since it's the abstract is public, we actually see around after 1.3 days, we see a 4.1 sigma excess over the background. So it's maybe not a strong detection, but it's close to a detection. I can tell you that it could rule out at least some of the models and have important constraints on late time distribution, late time TeV emission, which will break some of the degeneracy, but not all. So we need early X-ray and optical data, which we can probably get in the future for different bursts with Einstein probe and maybe this Spalding GeneWack telescopes. Okay, there's this lack of prompt emission, which is also important, but okay, I will just end by saying that, so we're, definitely, so we're in this, for the GRBs, we could say that we're in similar situations when blazars were first discovered in the gamma rays in the 90s. So we're seeing the component that's distinct from synchrotron emission. So we see how much the blazar field developed after the discovery of gamma rays. So we're in a similar situation for gamma ray bursts. And in the future, we could also hope to have, well, we could search for emission from the reverse shock, which has been predicted to be TeV, for which TeV emission has been detected. And we also need more data on the prompt emission, and this will break new ground. And I'm sorry, I've been quite out of time, but I'll put up the summary and yeah. And then end here. Yeah.
Thank you.
Sorry.
So we have time for a few quick questions. Over there, Jeff.
Hi, nice talk. I'm interested in knowing what is the fraction of burst, or you think, or you expect, that have a significant self-Compton component. So so know how many of them do need that emission. It's also important to know because the publications normally are of the detections, but there should be also strong, I mean, significant limits for some events that are also very important. Those that fall below what an excess of self-Compton would imply, and that's important for knowing how they're produced and where they come from.
Yeah. So, well, the quick answer is we don't know yet, but at least what we found. So when MAGIC detected the GRB, we looked at all the past observations, how much they followed up and could have been detected if they were seen in the right conditions. And it really seems that the conditions for, at least for Cherenkov telescopes, to observe them in a reasonably good conditions, very limited. So, and what we found is that actually it's, at least for MAGIC, it's consistent with all GRBs actually having similar TeV emission. And it just, we happen to be able to detect it when they were in the right conditions with the right brightness. So it doesn't seem to be, at least the one that was detected by MAGIC, to be particularly peculiar with respect, or when in comparison to other objects. But this is still, yeah, I mean, it has to be tested. We need more events. And yeah, so the wide field instruments, high duty cycle instruments will be very important for this.
I have one question with two parts. The first one is we heard from Howie yesterday that I mean, as expected, from the lack of publications or data on that direction, that LASSO has probably upper limits on other GRBs, but really not a detection. So the first part of my question is, from the point of view of a theorist, what are the expectations for a similarly sensitive instrument like LASSO to detect GRBs regularly, or where do we have to improve? And the second thing is, I mean, we haven't seen prompt TeV emission from such an exceptional event. Does this kill the hopes of prompt emission from GRBs at the TeVs, or maybe other kinds of sources could still store something?
Yeah, sorry, thanks. I was going to address this. So it's true that the upper limits on prompt TeV emission for this burst was really very stringent compared to the MEV flux. It's less than 10 to the minus 5. And I forgot to put the reference, but there's a work by Dai et al. With Shangyu Wang and collaborators who put strong limits on internal shock models if that's the case. But okay, so yeah, if it's similar for all GRBs, then yeah, unfortunately, it's not so promising. But as I said, the emission mechanism, the prompt emission, is the biggest open question, unknown question. So even upper limits will be very important. But I would so say that so this is still only one burst, and it was in a very exceptional, probably sort of an extreme kind of GRBs. So we have to see how much limits there are and more other GRBs. So I've been asking the LASSO people how strong are the limits on other GRBs that occurred in the field of view, which they didn't detect. We have to see, how sensitive the limits are on. But besides the prompt emission, though, there is also, I didn't mention it only quickly, but it's also possible that there's a emission from the reverse shock, which is probably more a short time scale emission, few hundred to few hours. And this is synchrotron emission. So it's possible that there is synchrotron self-competent emission there. Sorry. Yeah, from this region. Something similar. Okay. Yeah. To what we see in an optical. And this is something that's still probably challenging for Cherenkov telescopes. You have to follow up. So there are interesting prospects for this reverse shock emission.
But why don't you see X-rays so far, or didn't you see X-rays on this guy from the reverse shock? Are there data?
So the X-rays in the reverse shock. Well, okay. Sorry. It's true that they haven't seen, but probably I think in this phase, actually, the prompt emission is still quite bright. So it's like few tens to 100 seconds after the burst. The X-rays from the prompt emission is still bright. So there could be there is probably X-ray. Well, if there is a reverse shock, and there is probably emission that's, but it's just buried in the prompt emission. Yeah, that could be the case.
Last question by Alberto.
Well, it's not a question, just a quick comment. In Cork, we've been operating for 9 years. This is still work ongoing, but we are working on limits for generic GRB limits, and of course not as sensitive as LASSO, but it's, I mean, that GRB we would have seen, no doubt.
Actually, I forgot to mention.
So there has not been one like that in 9 years over our field of view.
So yeah, I skipped. So there is actually the Hawk limits on the boat GRB here, and this is actually itself is already constraining. It's probably in tension with the models by Zheng et al. So I don't think this has been published yet. Probably not yet, right? But this is still also important data. Okay.
So it's not yet published, sorry, not published. Okay, so let's move on for interest of time. Thank you. Let's thank Susumu once more. And then we move ahead with the next talk, talking about multi-messenger synergies with wide field of view ground-based gamma ray observatory by Sober Ratzak, Professor Sober. So now if we have the slides.
Okay, yeah, so thanks, thanks, Roberta, and thanks for the organizers for inviting me to give this talk. Again, I mean, this is a very broad topic, and I'll probably not doing justice in this 20 minutes. So I'll focus on quite narrow and more recent results in this area. So we all know about the multi-messenger astronomy, and we are living in a time when we have detected all the messengers that we know should exist, gravitational wave, neutrinos, of course, electromagnetic wavelength, and of course, cosmic rays. Right now, there are ground-based telescopes all over the world. Mostly in what I'm mentioning here is mostly in high energy gamma rays and neutrinos, also gravitational wave. And most recent one is this SWGO, which site has been selected to be in Chile. Okay, so the connection between gamma rays and neutrinos, that what I'll be mostly focusing on in my talk. So we all know about the processes that produce the gamma rays and neutrinos. So we talk about the leptonic processes, which are synchrotron radiation and Compton radiation, both by electrons. And usually no neutrinos are produced, although there can be situation when very low flux of neutrinos can be produced even in these processes. The main process to produce neutrinos are the hadronic processes, where we have a proton or ion. They interact with the surrounding radiation field, producing the neutral pion that can decay to gamma rays, and also charged pion that can produce neutrinos, and also energetic electrons and positrons, which can initiate radiation. Then the proton interaction that we also talk about mostly in the context of supernova remnant and dense target medium, where again you produce pions and which can produce neutrinos and gamma rays. So neutrinos and gamma rays are produced simultaneously in these processes. So one constraint to identify the sources where the protons are accelerated is that the gamma rays from, say, neutral pion decay or from electron positron in these hadronic processes, they are very, very energetic, and they immediately start a cascade process. So at the end, what emission comes out in gamma rays, they are much lower energetic then they are produced in these hadronic processes. But the neutrinos, on the other hand, they can be emitted almost at the same energies, at the same energy they are produced at the sources. So one challenge is to identify the sources based on the gamma rays only. That is why we talk about all this degeneracy between the leptonic processes and hadronic processes, because the gamma rays that we observe mostly are already quite degraded if they're produced in these hadronic processes. Okay, so the universe is filled with all sorts of radiation field at the very low frequencies. We know that there's cosmic radio background, and then cosmic microwave background, cosmic infrared background, optical, ultraviolet background that we know about, the X-ray background, and also the gamma ray background. But there is now, these days, there's also a neutrino background, and the neutrino background is quite low. You can see that these are the neutrino flux detected by IceCube collaboration, they're quite low, but they occupy very high energy space in this plot. Now, one advantage of neutrinos is that they can travel very far. Especially the gamma rays at the TeV energies and above, they interact with the background radiation, the CMB infrared optical UV radiation, and the very, very energetic gamma rays cannot propagate very far. So this is a plot of the gamma-gamma mean free path for energetic photons. And you can see that at PeV energy, the mean free path of gamma ray is limited to about 10 kiloparsec, which is the size of our galactic region. And we don't expect gamma rays above a PeV energy or so coming from extragalactic sources, or the flux would be very, very low. And also, at TeV energies, the gamma rays sources should not be high redshift sources. So this is what is called a gamma ray horizon of the universe based on some EBL model that myself and my collaborators, we developed some 14 years ago. And these lines are essentially the horizon line scale where that tau gamma gamma is 1. So at very high redshift, you can see that the optical depth becomes very large if you are above these lines, and then those flux from those sources would be severely attenuated. But neutrinos don't face this challenge. They can be coming from very far away. So that's why they can be a good probe to probe for very distant universe and very energetic processes. Okay, so let me now quickly update you about what is going on in the neutrinos. So most of the results in neutrino astrophysics that we know about come from IceCube detector. It's at the South Pole. It's been taking data for the last 14 years. And they have detected a diffuse astrophysical neutrino flux that I mentioned earlier. And there are two sort of flux models for this. One is based on what is called the cascade event. So electron neutrino and mostly tau neutrinos produce this kind of cascade events. And this is the event distribution as shown here. And this is dominated by, at low energy, is atmospheric neutrino flux. But this red histogram is the astrophysical electron and tau neutrino fluxes. And on the right panel, we have the muon neutrino fluxes shown as this magenta, this purple histogram. And their fluxes, the model, you can fit them with a single power law. And for the muon tracks, the power law is about 2.58. And for the cascade flux is minus 2.5. So they're a little harder than the observed cosmic ray spectrum, but that is okay, understandable, because the cosmic ray suffers some losses. It's the propagation effect, the diffusion effect that soften their spectrum. All right, so there are some confirmation by other neutrino detectors like Lake Baikal GVD in the Lake Baikal. They also detect a diffuse gamma ray, diffuse neutrino flux. That is the only or the first non-IceCube flux detected by other telescopes above 3 sigma. So their contours are still quite large because they're much smaller than IceCube. But as they collect more data, hopefully it will also improve. Then we have KM3net ARCA, which many of the South African universities are members of, and they are in the construction phase, and already they have analyzed their data from partial detector combining with their predecessor Antares experiment, and these are the sensitivity limit for their fluxes, and it is comparable with IceCube detected fluxes in neutrinos. All right, now let me talk about the sources, the neutrino sources that IceCube has detected. So the first detection came from this Texas 0506. It's a blazar. It was a very energetic neutrino, was in coincident with a gamma ray flare in 2017 from this blazar. So this is the location of the Texas, and these are the neutrino in the neutrino sky. And this is the gamma ray map from the Fermi Large Area Telescope. And this shows the overlap between the direction of the neutrino and the gamma ray. There has been a lot of modeling effort to explain whether this neutrino can be explained with the typical blazar modeling used to explain multi-wavelength emission, including VHE gamma rays from blazars. And for one neutrino event, this would be the flux upper limits, assuming that the flux, the neutrino is emitted within, say, 6-month time scale when the, for the calculation of the flux, and this is for 7.5 year time scale. And of course, it's whether the neutrinos coincident with the gamma ray is really a physical event in the sense that it is explained by this gamma ray SED, the multi-wavelength SED that also produces neutrino is a bit complicated because no model satisfactorily fit this neutrino flux required in this SED modeling. Okay, but IceCube also detected what is called a neutrino flare from the source about 3 years before the coincident neutrino event with the gamma ray flare. So that is that coincident event. But there is a detection of dozens of neutrino from within a relatively short time scale from this blazar in 2015, which is called a neutrino flare. Although there was no gamma ray associated with that flare, and that brings question whether these events are actually related with the flaring mechanism that we talk about in the blazar, that the neutrinos may not be producing the same flare where the gamma rays are, VHE gamma rays are produced. Then IceCube collaboration sends out neutrino alerts. There's a sky map of gold and bronze alert, right? Gold are a 50% probability that these are astrophysical neutrino, and the bronze is like 30% probability that they are astrophysical neutrinos. There's a follow-up community for this alert. And it's not only IceCube, but also Lake Baikal JVD. They have detected neutrinos, individual neutrinos from the sky. And interestingly, there's a neutrino triplet detected close to the galactic plane. Based on these alerts, people try to match with the blazar direction. And there are 4 blazars that seems to be within reasonable direction of these events. So this is, of course, the Texas, the PKS 1502, and this 3HSP source, and the GB6. One possibility in this work that my collaborators and I worked is that since these are pretty high redshift sources, it is possible that if the cosmic rays are accelerated in these blazars, then these cosmic rays, they can almost propagate along our line of sight from these sources and interact in the CMB and EBL and produce secondary gamma rays and neutrinos. And the secondary gamma rays and neutrinos may then be detectable by CTA and future neutrino telescopes. And the 2 sources seems in particular good target for this, especially the Texas source, where CTA really has a chance to probe this process and this 3 HSP source. Okay, now let's move on to non-flaring sources. So in the sky significance map produced by IceCube, they identify that there are 12 Seyfert galaxies in the X-ray catalog. They are kind of correlated with the significance, highly significant position in the sky. And that is about 3.3 sigma, excluding this NGC 1068. And 1068 is now established as a neutrino source. More than 70 neutrinos have been detected from this source between 1 and 100 TeV. So this would be the neutrino flux and from the source, and the gamma ray data from the source is over here. So there is a bit challenge now how to suppress the gamma ray produced in coincidence with these neutrinos to bring it down or sort of hide them to these lower energies. All right, now IceCube has also detected neutrinos from the galactic plane. So this is a significance map of this IceCube detected neutrinos. This is a very significant detection. But the flux of the neutrinos coming from the galactic plane is shown here. And compared to the diffuse flux, it is a factor of about 10 smaller. So of course, not all the neutrinos can come from our own galaxy. So but it is a sizable fraction of neutrinos coming from our own galaxies. And this galactic neutrino significance map is largely compatible with the diffuse gamma ray detected by Fermi-LAT and LASSO from the galactic plane. Now, speaking of which, I think there is a very good chance for these ground-based gamma ray observatories and like LASSO, as shown here, to detect very, very energetic gamma rays, which are essentially the same energy as neutrinos. All right, if we have, say, a pevatron, 100 TeV gamma rays coming from some sources, and we detect 100 TeV neutrino, so most likely this is a very significant event, and we can sort of tell that this is likely produced by the cosmic ray interaction, and these are the sources of the cosmic rays. So LASSO, located in China, and there has been some talks already in the previous session yesterday on this detector. And LASSO detected about 82 sources in the galactic plane within a latitude of plus minus 12 degrees. People are already working on this modeling, this gamma ray. So one modeling I show here is supernova remnant G40.5, and where we have data of covering gamma ray data covering a large energy range. So this is a proton-proton model trying to fit the gamma ray data, including the LASSO and HESS data. And this is the predicted neutrino flux from such modeling. And the current IceCube limit is shown here, which is just falling short a little to detect this neutrino flux. But the future telescope like IceCube Gen 2 will certainly be able to detect neutrino if these gamma rays are produced by the hadronic processes. Now, these authors also have looked into the list of dozens of LASSO sources, pevatrons, and kind of compared them with the sensitivity of CTA, LASSO, and the Tibet air shower array. And whether in gamma rays, they all can be more or less detected with all these detectors, including CTA. However, in neutrino, again, this the current generation telescope like IceCube is not quite large enough yet, but the future KM3net and IceCube Gen 2 will be able to detect neutrinos from these sources. Again, we heard about the Cygnus region detected by LASSO, very, very energetic photons detected from this region. And there's a modeling where we have the gamma ray from the LASSO and the Fermi-LAT, and where this is most likely this is from proton interacting with the molecular cloud surrounding the region and the gas to produce this gamma ray. So this is a model shown by the LASSO collaboration. But it is also possible then to have, say, neutrino emission, which is shown by this author in this paper, where we have a possibility that IceCube can detect neutrinos from this Cygnus region and validate the cosmic ray acceleration in this region. All right, so with that, let me conclude. We are now witnessing the birth of multi-messenger astronomy in gamma and neutrinos. We have 2 neutrino sources so far, and several other high significant sources. Future neutrino telescopes will probably establish other neutrino sources. And the counterpart of neutrino direction is ongoing in different catalogs, X-ray, gamma ray catalogs, even some radio catalogs, and they could reveal the sources of ultra-high cosmic rays in nature. And also, I think the galactic pivotrons are extremely prominent target to establish them as the sources of ultra-high cosmic rays by detecting neutrinos from them around the same energy as the hundreds of TeV photons detected by LASSO. Okay, and also not only in gamma ray, but also in neutrinos, there are a number of telescopes in the construction phase, and there's some proposed one which will cover essentially a very large energy range, TeV to EeV in neutrinos, and cover essentially the whole galactic plane by these neutrino telescopes, and will probably confirm this the galactic pivotrons. And with that, let me say that it's time to join multi-messenger astronomy, and thank you for your attention.
Thank you. So we have one question here from Rasmik.
Yeah. Thank you very much for the interesting talk. I have a question. So I think from the summaries given during these 2 days, we understand that there are probably something like 300 sources known for very high energy gamma rays. Yeah? And then you mentioned that there are 2 sources of neutrinos. And then I see a problem there, because fluxes of neutrinos and gamma rays should be very similar when assuming hadronic nature of the source. But now we see 2 sources against 300. So how do you explain this discrepancy?
Yeah, so this discrepancy you can explain by this attenuation in the background radiation. For the very high energy gamma rays, they are attenuated. So the sources.
But neutrinos you cannot attenuate.
So neutrinos don't attenuate.
So you have 300 gamma ray sources, just 2 neutrino sources. Neutrinos you cannot attenuate.
So these 2 neutrino sources. Okay, so at present the IceCube detector is not large enough. The neutrino flow. I mean, if you compare to the gamma ray telescopes and the neutrino telescopes, the area, I mean, or the effective area is not the right way to compare, because the cross section is so small. It's a million times smaller, actually, the neutrino telescopes compared to a gamma ray telescope, if you compare the effective area.
Or can I maybe reformulate my question in a more provocative way? Then I will ask you, could this be an indication that most of the sources are of leptonic character and there is a very little hadronic component? That's why neutrinos are missing.
I gave you the microphone because of line. From remote, they don't hear.
I mean, there's the isotropic diffuse flux, which can mostly come from extragalactic point neutrino. We also see the galactic plane, a large fraction of the galactic plane, but actually be due to the sources. And it's just that the neutrino angular resolution, I mean, the ice cube sections is not good enough to be able to resolve them yet.
But sometimes we should see some clustering, at least. I'm talking about 300 sources, not only of galactic origin. I think, do you think everything is okay?
So energy scale is also different, right? Remember that when you compare the VHE gamma ray sources, you are talking about 100 GeV and above. But those neutrinos cannot be detected by IceCube because there's atmospheric background is so high, you need to go to about TeV and above energy to detect those neutrinos. So even if these sources are, say, producing neutrinos, we will not be knowing this.
So you explain it only just by sensitivity difference.
Well, yeah, I mean, angular resolution.
No, flux should be comparable. In my understanding, flux of gamma rays and flux of neutrinos should be comparable.
At the same energy.
If it's a hadronic mechanism.
At the same energy.
Yes.
But I mean, you're mentioning 300 sources, but they go back to like hundreds of GeV, VHE sources, right?
Well, I think LASSO found, let's say, several dozens of sources at 100 TeV.
So
where are these neutrinos?
Those will be good sources, yes. So, but as I mentioned here, so these, for example, these authors, they have, so that none of these LASSO pevatron in the galactic plane, currently the IceCube is not sensitive enough to detect those. But in future, we should be able to detect those sources.
One possibility, yeah. Thank you.
Can you go to 1068, the SED you had? Yes, so that's a lot of neutrino flux. It has to cascade, the photons have to come from somewhere. So would it be in the MEV or where would they come out?
So it's a possibility that they might be cascading down to MEV energies, and you can see that there is kind of a gap in the detection in the MEV energy, and there are not many MEV telescopes at present, and this is one of the drivers for proposing future MEV mission.
Okay.
Wait, Susumu.
Yeah, Susumi's model is one.
Yeah, in our model, actually, we the cascade, well, there is, yes, expected MEV bright cascade emission, but it can go down all the way into radio, and it's actually explaining part of the emission detected by ALMA from the source. So depending on the magnetic field, that can occur.
Okay, thank you. From remote, I don't see any question, but please don't be shy if you want to speak up. And if there is no other question, then I would thank Sob again. And we move ahead with two contributed talks. The first is on cosmic ray propagation by Stella Faria. She's working at the University of São Paulo, no?
Yeah.
So in Brazil, and then she's also working in collaboration with Paris University. So please, cosmic ray propagation and multi-messenger emission by galaxy clusters.
Thank you for the introduction. So, good morning, I'm Stella. I'm PhD student at the Astronomy Department at University of São Paulo in Brazil. I hope you can see me. I'm a very short person, but go ahead. So it's the second part of my PhD project when we are investigating the cosmic ray propagation and the multi-messengers in the galaxy clusters. Our motivation is to understand the origin of the high energy cosmic rays, neutrinos, and gamma rays. Why? We want to improve, to have more accurate properties of the galaxy clusters using these multi-messengers. How? Okay, you need to wait a moment to know. So we know from previous work that these three quantities, the cosmic rays, the neutrinos, and the gamma ray flux, was measured by a lot of people. One of them are here, and they show this, the compared energy flux. So it can indicate that these quantities possibly can come from the same source, have a connection, let's say better, have a connection, or maybe came from the same source. And we continue this investigate in our research group in Hussein et al. 2023-21, when they use simulations to propagate cosmic rays in a band of galaxy clusters to get the energy flux of the neutrinos and gamma rays, and they compare with the observations. So the main results, that is, the galaxy clusters can be a very significant source for these diffuse neutrinos and gamma rays that are, when we listen in the last talk, are still an open question. So we have so many potential source populations. One of them, you have the individual one, like pulsars, AGN, gamma ray bursts, star forming. Here, we are talking mainly about source that can accelerate cosmic rays by first order Fermi process. Sorry, I always invert the words. So here you have this source that can accelerate these cosmic rays. But let's go back to galaxy clusters. Why? It's a so nice source. Because in this source, you have all the individual source insert inside of it. But you can also have the cosmic ray propagation in the intracluster median. So now we are not talking about the first order Fermi process, but the second order. Why? Here we are talking about the largest structure, gravitational bound from the universe. So it's very big. So the cosmic rays can be constrained inside of the source for a very, very long time. The second order is not so efficient, but you have time enough, believe in me, I know about the simulations, you have time enough to accelerate that. And let's add a piece of information, is to advertise time. So the intracluster median, when we know from the observation that is hot, is diffuse, has turbulence because you have so many processes happening inside of this environment, and it's magnetized. And it's very important, we already know from previous research that these magnetic fields are maintained by turbulent dynamo. But when you look the previous characteristics of this environment, say, how? It's a mess. You couldn't have the turbulent dynamo work in this environment. But we studied the solar winds, and we know from this environment that the same characteristics happening, and you have the instabilities appearing. And because of this magnetic field, this instability will influence a lot in the propagation of this, in the movement of this environment, and we can have turbulent dynamo. And I did this in the first part of my PhD project, and I will be so happy to talk about this after the section. So here in the first part, we produce a very accurate magnetic field in the intracluster medium, but we can talk about this later. Back to the cosmic ray propagation. I told you, you have two scenarios to accelerate cosmic rays. In this large environment, and you have the second order and the first order, the source. So to give my first steps in the multi-message environment, I start with the individual one. So we choose this simulation performed by Vaz et al. 2018, where they improved the resolution a lot when we can see, oh, I'm so sorry. Okay, we can see the increase of magnetic fields by turbulent dynamo. So this simulation was improved by Dominguez Fernandez et al. 2019, when she used these simulations to reproduce a bunch of galaxy clusters, and one of them, she used the same characteristics that we can find. They are very similar to coma clusters. So we selected and we use the Sierra-Propa tree to propagate cosmic rays in this environment, starting from the very simple model. So we are gonna cascade in these cosmic rays to get the flux of gamma rays and neutrinos from an individual cluster. So here you have a sketch of our simulation when you have the coma cluster with a source inside, and you're gonna propagate, and we're gonna follow this trajectory and deflection in the magnetic field background. And we know that the Sierra-Propa will do this propagation in a stochastic way. So we have so many interactions happening on that. And the principal ones, we can emphasize that you have the proton-proton interaction that you're gonna get us a pion that will decay to gammas and neutrinos, depend of if it's positive, negative, neutron. Like we can see here, you have these particles interaction with the background when you also got the pion. You have these gammas that are gonna be produced interacting with the gamma from the background, got positrons and neutrinos, and you also have Compton scattering. It was the main interaction that we included in our simulations. So here you have a very, very, very preliminary results, believe me, I put here. So you have the cosmic rays when we can see the first one. Look here, you got the observations from different spherical shells. So in the principle, you have a very flat one. And after, when you go far away, you can also see the magnetic horizon, and you can see a peak appearing here. So we have for the outer shell, the neutrinos. Here we were more worried about to see if the shape is agree with the previous work. And we have the gamma rays. But this one is not enough to see because it got in the shells and we don't observe close to the cluster. So we need to propagate. So the next step for my work, after I have enough statistics to do that, we are propagating these gamma rays up to the Earth. And when you have the main interactions by CBM and EBL, like I showed these equations before. So this graphic is coming soon, I hope. So it's my preliminary conclusions when we are trying to improve the previous work, when we try to get a more accuracy and more details about the propagation in an individual cluster. And that's it. I hope in the next one I can present all these results for you. Thank you.
Thank you, Stella. And good luck for the results in the future. Is there any questions? I should check. Sorry. So let's thank Stella again. And since we are a little bit later time, if you have questions, you can contact her offline. And then we move to Antonio De Ugarte Postigo from CNRS. He will be talking about gamma ray burst again, but this time from a different perspective. So it's clues from the host environment.
Hello, and thank you for staying until the end of the session. So yeah, my name is Antonio De Ugarte Postigo. I'm working in France right now. And I'm going to speak to you about gamma ray bursts detected at very high energies, but from another perspective. So we studied one of the first ones ever detected in very high energy photons with magic. In that case, it was 1901 14C. which happened to be it was a normal GAB, apart from the detection of very high energy, but it happened to be in a very peculiar environment. So we decided to have a look if environment was actually an issue for generating those very high energy photons that we are detecting. So we've already heard a very nice introduction to gamma ray bursts and how their radiation is produced. I'm not going to go very much into this. As we were explained, we have a central engine, which different kind of progenitors can be a massive star or a binary neutron star merger. And we have a very relativistic, ultra-relativistic jet in which internal shocks can produce the gamma rays, the prompt gamma rays that identify the gamma ray burst. And an external shock when that material that is ejected decelerates as it interacts with the interstellar medium. There can be a reverse shock as that material bounces back towards the jet. And it can be followed by either a kilonova for a merger or a supernova for a massive star. There has been also identified a cocoon associated with the emission that is difficult to see normally because of the afterglow, but that's not something that we care about in this particular talk. The gamma ray burst, this prompt emission, is followed during that interaction with the interstellar medium by a synchrotron emission, and that's what we normally see, and that's what we can follow for hours and days after the GAB. From that, we can derive the particularities of the microphysical and macro and microphysical parameters of the explosion and its environment. There can be a reverse shock, as we said, and what's more interesting perhaps to us is that in some cases there's also a self-compton emission that is probably what's contributing, at least in some of these cases, are the very high energy photons that have been detected. So that's an important component that apparently is not always there, but it can be a strong contributor for the emission that we're looking into. The problem that we have here is that gamma ray bursts are quite high redshift events. The typical redshift at which we detect them is around 2. So this is not so easy for gamma, very high energy photons, which get attenuated at higher redshift. So we are quite limited into the redshift that we can explore. We're just looking into the nearest gamma ray bursts. So this was the first one I was talking about, and that was at a redshift of 0.4. So what we are doing in this project that we are carrying on now is look at the local environments at the host galaxies in which they are produced. These are the 7 gamma ray burst host galaxies. So the 7 GABs for which we've had very high energy detections. One is a short gamma ray burst, and there are 6 others. So we have enough to do statistics, though we not. When we have more than 5 or so, we can start thinking about statistics. We're gonna mostly remove the short gamma ray burst from the study because it's a different kind of progenitor and because it was a very low signal to noise ratio detection. So that's a bit more discussed. So we're gonna focus on this long gamma ray burst produced by a massive star collapse and look at the environment. This was the first one I was talking to you about. It was in a peculiar environment because it was in an interacting system of 2 galaxies, and it occurred very close to the core of that of the host galaxy, with a lot of with a high density and a lot of peculiar lines in the spectrum when we looked at it. However, when we look at the variety of other GABs that we have, they are quite diverse in the kind of galaxies that we can have here. A very massive elliptical galaxy. We can have more irregular galaxies, compact, and so the circle in each of these galaxies is the same size. That's 1 kiloparsec radius for comparison. So what we've done is perform photometry of the galaxies in optical and infrared bands, also with mid-infrared and ultraviolet data when they are available, and do spectral energy distribution fitting to try to get the characteristics of the host galaxies to see if those host galaxies differ from the ones in which other gamma ray bursts are being produced. And this is a sample of properties on gamma ray bursts. Typical gamma ray burst is a large sample, the largest that we have right now, comparing the redshifts of the big sample with the ones in blue are the sample, and the ones in green are those of very high energy detections. You can see that the redshift distribution is very different because of the attenuation that we have a higher redshifts, but the other properties are not so strikingly different. However, since this is not a completely fair comparison because of the redshift distribution, we've limited the sample to those that are in the same range. And if you look at those, the differences are perhaps even more subtle. There's the same amount of extinction in the host galaxy, the similar stellar mass, maybe a little bit more, but nothing significant, because the uncertainties are quite extended. This is metallicity, this is star formation rate, and this is age of the population, which could be a bit older, but with this small amount of objects is not that significant. In any case, we looked at the offset. As I said, the first one happened to be within the core of the galaxy. So what we do is compare the distance of the GAB location with the R50, so the radius that contains 50% of the light. So we can compare galaxies with different sizes. If you look at the green, our very high energy sample with other GAB samples, there's no difference. So that initial aspect that we had of this first burst that happened in the core it was just one coincidence in this sense. However, even though the host galaxies don't seem to have any particular difference, when we look at the line of sight using, for example, spectroscopy, the spectroscopy that we get from these GABs are punching through the line of sight towards us. So they are sampling very well all the material that is in the middle of the wave. And here are some diagrams that compare. In black is the typical strength of absorption features, and in red the absorption features determined in a particular event for the sample that we have. There are very few lines, and if you see, only the reddest lines are there because of the low redshift. These are lying the ultraviolet. So the average is slightly stronger than the sample, but it's not very significant. So the percentile will be around 64, so it's not very different. But there's one thing that stood out when we look at the spectra. There's a significant amount of excess of sodium lines as compared with the sample. That means that in the line of sight, there seemed to be a bit more material of some kind of material than in other GABs. Sodium is also associated often with dust in the line of sight. So if we actually look at the dust in the line of sight, the one I showed before is dust in the global galaxy. This is dust within the line of sight. There is a bit more dust than what we see in other GABs. But what is also interesting is that the relation between the extinction derived by sodium lines implies that there will be much more extinction. So these sodium lines are a peculiar feature of this sort of very high energy photon events. So that's something that we still need to look at. As I say, the sample is very small, and actually in one of them we don't have the spectral range to study it. But it's beginning to show that there might be something within the line of sight that is slightly different. One other thing that we've happened to find in two of these events, actually one of the two first ones, well, actually there was one before but was not announced until afterwards, is the detection of diffuse interstellar bands. The diffuse interstellar bands are also associated with dense environments. We detect them in the Milky Way. It's not very clear what they are associated with, although there are some molecules in which they have been correlated, some individual ones, but not all of them. And these are the first two gamma ray bursts in which we have detected dips. So the fact that the only two in which there are dip detections are also two for which the very high energy photons have been detected also tells us something about a perhaps peculiar environment. So the conclusions I'm going to leave here and let us all go to lunch. The host galaxies are not very different, but there seems to be some peculiarity beginning to show up in the fact of the local environment, the extinction, especially sodium and these particular dips that have been detected. So we just need more examples to get this statistic growing. It's also important, as I mentioned before, that we get also limits when they are significant, if they exist, so we can make those numbers in a more statistical way. Thank you very much.
Thank you, Antonio. So we have one quick question by Susumu.
Yeah, interesting results. Not sure what to make of it, but but what I'm going to ask, so 1908-29A is a little bit different from the others, and that's rather low luminosity. Maybe it's not really low luminosity. Some people classify it as intermediate luminosity, but it seems to be different than the classical. So are there any things particularly peculiar about this burst compared to the others, or is it?
Well, this is one of the two for which we have dips. So it is a peculiar environment. The host galaxy is the largest host galaxy that we know in the local GABs. So it's a very, very massive galaxy. But it is located, if you look at the picture, well, it was actually that one, it's located quite far from the core. So it is sort of different. And the environment seems to be different also. So you can see also here there's sodium excess in that one. So it's true. There's a lot of variety on the, and that's also something surprising. There's a lot of variety in the kind of GABs, and you mentioned it in your talk, of the different GABs that we're seeing. But there seem to be some common grounds in some excess of sodium and perhaps extinction and dust in that environment. How much of that is local? That could be, the sodium detection could be an indication of a more local dust than host galaxy dust. So it's something, I mean, we need statistics, but this is the first hints that there might be some things enhancing that upscatter of photons to the very high energy range. I'm just approaching this from a purely observational perspective.
But in this, I mean, along this line, you are concentrating on the 6 that have been detected at very high energies.
Correct.
But to some extent, I mean, you have also all the Fermi-large GRBs with high energy. So why don't you use those? I mean, you may select on the highest photons ones, but you may increase using Fermi-large.
Yes, and I think that's something that we should do. Now we've just focused on the very high energy photons. But it's true. We should look at it to see if there's also a difference in those Fermi-lat with giga electron volt detections, and if there's a transition, maybe there's a transition towards there. So yeah, this is a just ongoing work, and yes, I agree with you. Thanks.
No, that's very interesting. So let's thank Antonio once more. Apologize if we are a little bit late. I want to thank all the speakers of the session. We reconvene here, right? At 1:30 in 1 hour and 10 minutes.
bring it to us on the flash drive.
But you have all the speakers list now.
Got the list, but
Yeah.
if we don't have the slides,
Okay.
I can't do anything.
Right.
So the simulation for this.
How is the situation now?
Just want to show you how the microphone works. Simple, yeah. On.
All right.
Oh, so I think the problem is it's the only.
Can we get this? Okay. Here, Robert, I'll give you a 10-minute and a 5-minute warning.
Perfect.
So your talk is 30 minutes, but 25 plus 5. All right, let's get back into session. So we have 5 talks, 2 invited and 3 contributed talk. The first talk will be given by Roberta Zanin, and it's going to be about synergies with IACTs and CTA. Okay. Go ahead, Roberta.
Okay, so good afternoon, everybody. So I'm Roberta Zanin. I'm the project scientist of CTA, so the Cherenkov Telescope Array Observatory. Ulysses, when the SOC invited me, the title was Synergies Between Particle Array Detectors and Imaging Atmospheric Cherenkov Telescopes. So here, after having looked at the agenda of this session, I thought, okay, since we had a lot of many excellent talks on science, I will focus more on the performance, let's say, instrumental part of these synergies, with the main goal of the talk to really transmit the message that there are 2 different techniques, but they really work in a complementary way. So let's see if at the end you will convinced by these statements. So I have, the talk is basically divided into 2. One will really focus on the currently existing instruments and the detection techniques, and then the second part is on the future. I mean, given the audience, I don't need to I will be faster on the introduction. So very high energy gamma ray astronomy, we are talking about a field that is at the end at the highest energies of the electromagnetic spectrum, that was born as astroparticle physics. So it's really at the crossroad between high energy particle physics and astronomy. And the reason for this lies in the detection technique. But despite the fact that behind us there is a detection technique that really comes from the high energy particle physics field, the goal of the astroparticle field and the gamma ray astronomy in particular is astronomical. So it has many implications. What we are looking at are extreme phenomena that so violent phenomena in extreme environment that produce non-thermal emissions. So these non-thermal emissions that optical, radio, X-ray astronomers are looking at for their scientific projects, they also emit high energies and very high energies in particular, mainly through the inverse Compton mechanism. So you can combine, you can use the gamma ray data to infer further information to the mechanisms that are producing your emission, the emission of your sources. So it's really important to keep in mind that very high energy gamma ray astronomy can be used as one of the fields of the astronomy. And I think, I mean, this field was born in the 90s. So 1999 is the official date with the detection of the first source, but it took a while to really prove that the detection technique is actually successful. And I think now, I mean, in 2024, we can say that we really reach the astronomy status. So what does this mean? So we moved from detection machines experiments with private data, proprietary data, and working really in an experimental environment to something that is ready to become an astronomical observatory. And we will see it in a second. So when I talk about gamma ray astronomy, there are two main fields. One is subfields. One is the GAV, what we call the high energy emissions, and the TV, which is the very high energy gamma rays field. So at the moment in GV, we have, thanks mainly to Agile and Fermi-Lat satellites, we have more than 4,000 sources. So we increase by 2 orders of magnitude the number of detected, 1 order of magnitude the number of detected sources with respect to the previous generation of instrument in this energy range. And we have angular resolution sky maps with few arc minutes energy spectra that goes from 20 MeV for 4 decades in energies. At TV, instead we have more than 20 almost 300 sources at the moment with different, more than 10 different source classes. And the resolution is very good. It's in TV, so we are at the level of arc minutes with spectra that spans from 30 GeV for 3 decades in energies, and time resolved light goes down to 2 minutes time scales. So now we know that I come back now to the detection technology. So the gamma rays, we know that the atmosphere is opaque for gamma rays. So either we send a satellite, and this is what you do mainly in the high energy range with the detectors like Fermi-Lat or Agile, or but they have a constraint that is related to the maximum effective area that you can get with a satellite. So if you really want to increase the effective area of your telescope, then you need to go to ground. And then this is possible because we use the atmosphere as part of our detector. So the atmosphere becomes the calorimeter of our detector, and then we can indirectly detect the gamma rays. So what happens is here is that the gamma ray interact with some molecules of the air and produce cascades, what we call the extended air showers. And these cascades, so the first interaction almost happens above 12 kilometers above the sea level, and then extends, and some particle extends for almost tens of kilometers, but some particles, the highest, the more energetic ones, really can reach the ground. So these are first orders numbers that will be used, that we can use them in the follow-up of the talk to really understand the difference between the two techniques and how we can improve these two techniques. So now, how do we detect these cascade of particles? So there are two ways. Either we measure the particles, and then we have what we call the particle array detectors on ground, or we use the Cherenkov light that these particles are producing when moving at a speed of light, at a speed which is larger than the speed of light in the air. So, and this would be the detection technique of the imaging Cherenkov telescopes. So now I think, I mean, in this audience, we should know almost everybody should know the detection techniques, but here the main point I want to make is that the ICTs, so the imaging Cherenkov telescopes, are pointing instruments, and they detect Cherenkov light, which is a light in the optical UV energy range. So they are special kind of optical telescope. As such, they only work during night. And so this means that they have a relatively limited duty cycle, about 15%. The field of view is for this generation of instruments is about 3 to 5 degrees, and with an energy threshold of about 50 GeV, with a maximum energy that it really depends on the statistics, but just to give you a number, is tens of TeV. And then of course, the more you integrate, and depending also on the flux of the source, you can reach higher energies. So IACT, keep in mind that they have duty cycle 15%, field of view 5 degrees, and they go from 50 GeV up to tens of TeV. In the particle array detectors, we have, so these are detectors that can look at directly at the particles, and we will see in a second how these they work. But these are the detectors like, for instance, LASO and Zwigo. You have heard about them. So the duty cycle in this case is 100%. So they are always looking at the sky with a field of view which is a steradian field of view. So they are looking to the sky that passes through them, with an energy threshold which is higher. So for the current generation is about 1 TeV, and then it goes to few hundreds of TeV, with the same argument that the maximum energy is always limited by statistics. So here I have emphasized the numbers, the performance parameters that in red that can be improved. So when we will be talking about the future generation of both IACTs and particle array detectors, we will be looking at these parameters to see how we can actually improve them, and what's the reason for these improvement. So this is a nice plot by the LASO collaboration that was done in the context of the both these brightest of all time GRBs, that shows the difference in the field of view. So the from LASO Oak, you see, so the particle array detectors versus the pointing instrument, the ICTs. So you see there Hess, Veritas, and Magic. So just to give you a feeling. So when I will be mainly concentrated on the, I didn't mention you before, sorry, about that, that I will be concentrating on the very high energy part. And then I will be talking for this first part about the 3 existing facilities of this kind. So it's what we call the second generation of ICTs that are operating since 2004, more or less. I mean, Veritas came a little bit later, and these are Veritas, Magic, and Hess. And then we have also the second generation of particle array detectors that they came online 10 years more or less after the second generation of ICTs, and we're talking mainly about Hawk and LASO. So, okay, so that's the galactic equator. To see what I want to stress with this curve is mainly, you see that here in this plot that most of the facility that we have now are concentrated on the northern hemisphere, and there is just one at the moment in the southern hemisphere. So then we are lacking part of the capabilities from the southern side. So these facilities, I think they have, as I said at the beginning, they have proved that they are successful. And I think from the imaging atmospheric Cherenkov telescope point of view, one of the main achievements was the excellent background rejection power. So that, and this really improved in the last years and is keeping improving thanks to the usage of machine learning techniques. We have large collection areas. This is given by the fact that we use the stereoscopy, so more than one telescope, but also large zenith angle observation for the small arrays are very helpful to increase the collection area. And then we have set up a system of monitoring the Earth atmosphere. I said at the beginning that the Earth atmosphere is part of the detector, and is something that we cannot control. So we need to monitor the atmosphere as much as possible to be able to keep under control, to correct the data eventually, and keep under control the systematic uncertainties. The other important point that really made some of the success of this technique is that we reached to go down to tens of GeV. So this is strictly related to the fact that the lowest energies gives you access to a volume of the universe which is much larger, so that the universe becomes transparent. So you can look at up to the dawn of the universe at around 20 GeV to give you a feeling. From the operational point of view, with this generation of instruments, we managed to have real-time analyses that really helped in the time domain astronomy, so to set up and to follow up alerts coming from other wavelengths. And then there is a point that we never mentioned, but is there. So at the beginning, when all this started, we were thinking that the very high energy sky was not very much populated. And instead, now we have 300 sources. And we did basically the same mistake. So the same thinking when we were thinking to the ultra high energies, so something like hundreds of TVs. And we were thinking, okay, but I mean, there must be few sources there. Instead, one of the success of the particle array detectors that are now operating, so Hawk and LASO, is really to have proven that the TV sky is very much populated. So we have more or less 100 sources even there, and other. I mean, just to be complete. So even the particle array detectors managed to reach a good background rejection. Is not at the level of the imaging array Cherenkov telescope, but still, I mean, it's improving a lot thanks to the machine learning again, but also the usage of muon detectors. And they also have, I mean, for the same principle, they have a large collection areas, and they have really an astonishing and impressive sensitivity at tens of TeV, which is a window that has been unexplored until a few years ago, when because of what I was saying, there were only arrays of IACTs was let's say maximum energies was around the tens of TeV. So from the perspective of the performance parameters, so this is a plot that you will be seeing it in this presentation. So it's the differential energy sensitivity as a function of the energy. And you see there are IACTs, so this is an average sensitivity curve considering the three facilities, so MAGIC, HESS, and Veritas. And this has been computing for 50 hours of observation. And then you compare it with the LASO and the Hawk source. So the LASO sensitivity for 1 year and the Hawk for 5 years. So here the message is you see that there is an overlapping energy range between one few TeV up to tens of TeV. And then there are energy ranges which are more focused on the particle array detectors capabilities or on the IACT's side. I mean, there are always two main performance parameters when we look at these kind of instruments. So one is the sensitivity, so the capability to measure the minimum flux of one source, but is also the resolution power of these instruments. So here you have the point span function. This is a figure that you saw this morning. By Marcus. So this is Centaurus A detected whose extension has been detected by Hess. And you see here in the circle, the black circle is the Hess point span function at 3 TeV. And then this is a in scale sketch to show you the point span function of different instruments at different energies. So you see the Fermi-Lat Hawk and how this compares, for instance, with LASO point span function. So on one hand, we have extremely good detectors at the highest energies. On the other hand, we have extremely good detectors at the low energies. In the middle energy range, I mean, they are overlapping with good sensitivity or comparing sensitivity, but we need also to keep in mind that most of the science needs, or precision measurements needs, the angular resolution. So it's really a matter of where the two techniques can be complementary. And I will show you few cases where this became striking, and I think it became clear already this morning in the session we had. So when I always talk about science cases of the very high energy astronomy, I usually divide them in sub energy ranges, so the sub TeV, the TeV, and the multi TeV, which kind of resemble this plot that I have just shown. So you see here that the sub TeV one is mainly is a main important field for the energy range, for the IACTs. The multi TeV can be reached by the IACTs, but there is the main science cases for the particle array detectors, and then in the TeV there is both of them can have the same science cases. Just bear in mind that when I list here science cases, these are the science cases that are dominant for that energy range. But this doesn't mean that if I want to look for transient or cosmological sources, I can see them only in the sub TeV. So I would need the capabilities of the instrument in the sub TeVs, but then of course it helps and adds a lot of information if I can detect also in the neighboring energy ranges. So here, so in the sub TeV, we have mainly transients and cosmological sources. So these two phenomena are strictly correlated between each other. And the main reason here is that gamma rays are, so the universe is not opaque to gamma rays. They are absorbed by the EBL. So then if we really want to see distant sources, we need to go as much as possible down to the in energies, and up to the 20 GeV, where the universe becomes again transparent. We have pulsars. You know, the pulsars were not supposed to be very high energy gamma ray sources. Actually, it's one of the discoveries of the last years of the IACTs, of the currently existing IACTs. We have been proven that pulsars are emitting very high energy emissions above the curvature radiation that was foreseen and was detected in the standard scenario of the pulsar emission in gamma rays. So there is another component, and this plot here is the Vela pulsar published by Hess last year, that really proves that this emission comes from a different component. So it's an inverse Compton component above the curvature emission that you see here in Fermi-Lat. So but it's not the only important results that we had in the last years, and they really open and enforce the science case of these fields, we have the detection of the gamma ray bursts. I will not talk about them because Susumu this morning talked a lot about, but these were first detected in 2019, and now we have, we saw this morning, six gamma ray bursts already detected. We have another important, so this is the first scan of the galactic plane. So this is a combination of the Veritas GPS, so Galactic Plane Survey, and the HESS one. So this took more than 4,000 hours in total to reach this level. And then another important discoveries of these last years that really increased the importance of the fields are, on one side, the Pevatron discovery from both Hawke and LASO. Here you see the LASO Nature paper in 2021 with the first 12 sources reaching PeV energies, and also the detection of microquasars. So this is the extent. So it's not the emission from the core of the microquasars, but from the interaction of the jets of the microquasar with the interstellar medium. And you see here, this was a discovery of the Hawke collaboration. So this to say that both technologies really helped in opening up new windows of exploration for these fields. And what is even more important is that until let's say the 2010, there were only arrays of ICTs, no? And we saw before that they have a field of view of 5 degrees. So basically there was a strong observational bias towards the extension of the detected sources in very high energy. So they were all 2 minutes? Okay. So the it's important to see that these sorry. Okay. So the extension was so the IACT were not detecting these kind of sources because they were too extended. So then after the detection by Hawke of Geminga, this is 1 degree extension sources, then the currently existing facilities really helped in so really improve their detection technique and managed to detect these kind of sources. So here we see the importance of the synergies. So where the two techniques could really play together, and we managed to learn one from the other. The other example is what was mentioned this morning by Marcus. So this is a low luminosity AGN. So nobody in the IACT world would have pointed at this source. But now, thanks to the survey capabilities, we enlarge our knowledge, and we know as IACTs that we have to improve our triggering and our observational strategies. The other aspect, this is more focused only on ICTs only, because it came before, let's say, the discovery of LASO gamma ray burst. But for 20 years, we tried to look at gamma ray burst and we failed with ICTs. Okay, on one side, there is okay, we were waiting for the right event. But on the other side, we have to acknowledge the fact that we also did the wrong choice in the observation triggering and the observation strategies. So this is the low luminosity gamma ray burst, whose detection arrived almost 5-6 hours later. And the first time we saw the gamma ray burst, so this was the second gamma ray burst detected by HESS, that the first detection arrived 10 hours later, and it arrives 10 hours later, not because they were looking at, but on purpose, but it was the first time the source became visible at the HESS site. So we really need to learn from the past to improve our observation capabilities, but also we need to improve from the two different technologies. So a bright future is really coming and is above us. We saw, I want to mention mainly, I mean, there are plenty of facilities. I want to mention 2 of them. So CTAO that has 2 sites, one on the north, so same site of MAGIC, and one on the south. So CTAO is this Cherenkov Telescope Array Observatory that is really going to be the first ground-based astronomical observatory. So this means that it's a proposal-driven observatory that has been conceived as an array of ICTs. So as such, so the decision of this instrument was based on this technology, so the array of ICTs, and as such, we know that we need a site which is around 2,000 meters above the sea level. So the drivers of the CTAO designs are the following. So we know that this technique is successful, but we want to have something which has a larger field of view, at least 10 degrees. We saw that I proved with Geminga, for instance, that we need a larger field of view to study large scale structures. And this is very much related to the telescope design. We have a full sky coverage. So we want to have at least 2 array sites. Then want to go down to the 20 GeV for the reason I mentioned before, and up to 300 TeV or even larger. So the low energies are related to the dimension of the reflecting surface. The highest energies are related to the array footprint. So here you see, so that's the main idea is, okay, let's use IACTs as we know that with the design we have, but let's increase the number of them to increase the collection area, so the footprint, and then we can really reach the highest energies. It's not as simple as that because sorry, okay, we have 2 sites as I mentioned, but it's not brute force and then just you have a design and increase the number of telescopes, but we really optimized the design of the telescopes per energy range. As I showed you before, each energy range is focused on a set of science cases. And here the idea is that in the sub-GeV, where we really want to have the lowest threshold, so the 20 GeV threshold, we need to have large detectors, so large reflective surface, but we don't need many of them because we have plenty of gamma rays at these energies. So you know that the gamma ray spectrum is very steep. On the other side, on the other extreme, if we want to reach the multi-TeV energy range, we need many telescopes to cover a large footprint, but they can be small telescopes. And this is also a way to have a cost compromise and so to optimize the cost effectiveness of the instrument. So here you see what I have just said, basically, that there is the array with of telescope with the large size telescope in the middle, a ring of workhorses, a middle-sized telescope, and then SSTs farther out in the outer ring. As you see in the sketches, so the distance between the telescope is not always the same. Why? So here the reason is related to the other drivers of the design, which are the angular resolution that we want to improve with respect to existing facility down to sub-arc minutes, angular resolution, and we want to have a sensitivity which is at least a factor 10 with energy resolution of 10%. So all these basically are related to the fact that we need a denser array to improve the background rejection and also the angular resolution and energy resolution. There is another point that is important, energy scale, systematic uncertainty, and this is related to the atmospheric characterization that I mentioned before. So here you see the layout of the fully funded initial configuration, what we call the alpha configuration, in the south and in the north. So the northern part is much smaller than the southern array, whose footprint is 3 square kilometers. And I want to mention that in the south, although I mean this is what has been agreed by the funding agency, we already have an upgrade in the pipeline, which has not been formally accepted by the council, but it's already there. So we know it. We are sure it will happen. So we will have large size telescope also in the southern side. So Astri, I will skip it. Giovanni will talk about this. The SWGO. Here I was doing the same exercise. Now I'm running out of time, but the same exercise for that I did for CTA also for SWGO. And in this case, we want to go down in energy. So it means that we need a higher sites, we wanted to have a larger footprint to increase to the energies up to the PeV, and then the same logic of the denser array applies for these performance parameters, angular resolution and sensitivity. So here you see that the point of SWGO is to have a core which is as big as Hawk now, and then an outer ring which is of the order of 1 square kilometer. So here I skip these, but just to say, you see that the core part is much denser, and then the outer ring is spread out, and the principle is exactly the same as for CTA. So here there are also mixed detectors, as we saw yesterday for the case of LACT. I finish with this. I mean, I want to show you steady performance. I mean, this is for the northern hemisphere. So you have what we will have in the future. So these are the usual curve we saw before. So ICTs, LASO, and Hawk. And then overlay, we see also ASTRI and CTA North. So I think it is important to make a point. When you look at the sensitivity, you usually look and we plot the sensitivity for ICT of 50 hours of observation. This is because this is the average observing time that we use in the proposal for the current existing facilities. But here it really depends on the science case you want to address. So for instance, for ASTRI that is focused on multi-TV, so pivotal searches, they will focus on few sources. And in this way, then they will have what is relevant for them is to look at the sensitivity at 500 sources. It will take a few years for them to get 500 hours of observation on one sources, but then this is what their goal for that specific science case. So this is one point that we often forget. And then the other point, you see here the same comparison that I was explaining before. So how ASTRI and CDA can really improve the angular resolution in this energy range. So for the southern site, you see here overlaid also CTA South and SWGO. And you see what I was mentioning before. So the sensitivity at the highest energies is dominated by particle array detectors, where the performance is dominated by IACTs. Here you have, and I leave it there so you can look at the angular resolution. And then I come to the conclusion. So this is as last slide. So when I said that the future is very bright. So this is what will happen in the next, let's say, 8 years. So we have still MAGIC-S and Veritas running for a few years. In the meanwhile, CTAO is really starting construction, and we plan to have so the first intermediate configuration running in 2027. About the same time, LACT will have the first telescope, and then it will both CTA and LACT will be full at the end of the 30s. ASTRI is supposed to start taking data next year with the first telescopes, and then in parallel we will have LASO and Hawk running for a few other years, and SWIGO that is still on the design and planning phase that will start in around the end of this decade. So just mention the end dates of the facilities are really indicative. So it's the fate of these instruments is still under discussion. So don't take it as a real final date. And I leave the conclusion here. Sorry for the.
Okay, we have time for 2 very quick questions.
I think this is a comprehensive talk. Thank you very much, Roberta. And then my impression, it described the current situation and then near a few years very well. But I myself, I have a fantasy. I can imagine that these particle detectors can lower the threshold by another order of magnitude. But what they should do, they should complicate individual detectors. But if they go for it, which means money, I can imagine they can go down to 50 GV or even lower.
Sorry, can you reput my slide?
Yeah.
Because there is a plot there.
Yeah.
They are already working on. I mean, Ulisse can certainly comment better than myself, but they are already working on this.
Maybe.
Well, okay, we can talk offline if now.
Hi, thanks for the incredible talk. Just wondering, one of your slides, I saw you put dark matter as a source of TeV energies. Is that like speculation or like?
I mean, in the TV is where we will be very competitive with respect to Fermi, for instance. I mean, this is a window that has not been yet explored by Fermi-Lat. In the multi-TV is where the particle array detectors will be more competitive for the dark matter searches.
Oh, so it's like speculative at the moment, or like
research. So far, we're just, I mean, so we're talking about in terms of what we can constrain for the different models. Then if we will detect, this will be great. But
all right, so with that, let's thank Roberta again. So the next talk will be by Giovanni Pareschi about ASTRI array.
Okay, thank you. So this presentation is becoming very challenging for me, first of all, because I uploaded, I realized when that I uploaded before my presentation in the conference in the other room. And I realized also that I have more slides than Roberta, and I have to shrink in half of the time. So thank you for giving me the opportunity to talk about the mini array. This is a project that started about 10 years ago, led by HINAF, but involving, you see, a number of international partners, including the Northwestern University here in South Africa, and the São Paulo FAPESTA in Brazil, and in Spain, ESA and the Fondazione Galileo Galilei. And well, we started with the idea to consolidate the technology in view of the implementation of the small size telescope array in CTIO, and we developed for that, we will see in a moment, specific small telescope with wide angle working in atmospheric Cherenkov. But then we started to develop this mini array that initially should have been part of the southern array of ASTRI, but there was a mismatch in the program. But we can see that, by the way, now the ASTRI design for the telescope has been adopted with just minor changes for the SST array on CTO South. So the telescope are working for Cherenkov in air, in the atmosphere, but they have a quite big field of view, more than 10 degrees. And this is thanks to this design that was never tested before, was proposed by Vladimir Vasilyev about 15 years ago. Is also adopted in a prototype in US. This actually is a design that normally is used for X-ray telescopes, for example, Chandra, or before Chandra, Einstein, or XMM. But never tested before is an aplanatic telescope, giving the opportunity to have a larger field of view with also a decrease of the play scale. So in this way, we can work with very small pixels, like the one allowed with the silicon PMs. So I joke very often, you know, this is the fantastic primary of the James Webb Space Telescope. You know, each of these segments cost more or less 2 billion of euros or dollars. In our case, our segment cost more or less 2 kilo euros, so 2,000 euros, but we hope to do very good science as well. Well, but the secret is the possibility of producing the mirrors via replication in order to have a mass production as needed, but also one challenge was the production of the big secondary mirror, which has to be used for this wide field telescope. And this was done after several trials via thermal slumping, while for the primary we use a sort of cold slumping, in the sense that we freeze the shape after a replication from a master. Okay, you have seen that before there was a telescope, but there was a prototype developed for demonstrating the technology. It's an end-to-end telescope developed and installed in Sicily on the Etna volcano slope. We had a lot of fun. For example, thanks to the very big field of view, we are talking about several degrees. In this case, more or less 8 degrees. We are able to catch cosmic rays also big size, as the ones simulated, for example, by Razmik some times ago. And you see that we are able to catch also irons, or in any case, a big shape telescope. But this prototype allowed us to demonstrate something very important. First of all, the fact that we have a field which is flat across a field of view in diameter, which is more than 10 degrees, completely flat. You see, the PSF stays into the pixel, the side of the Cherenkov pixel side, and without moving. And the second is the first demonstration of an observation of a gamma ray source, in this case the crab, with a dual mirror telescope. And this was not obvious, of course. So at this point, we started the implementation of the mini array. The mini array, in a nutshell, is something is being developed and implemented in Tenerife at the site of the TED Observatory, where there are also many other small telescopes. It's not the same islands of CTO North, which is La Palma, but is pretty close. And I mean, it's the same community in any case, and same institute running the site. We have another site. An important point is that we are playing with a very small amount of data, less than 3 terabytes per night. And every night we are able to transfer all the data to our data center in Rome, where we can make the post-processing and the software triggers, secondary trigger of the mirror. We have a white book we have prepared. I invite you to these are open source papers. One is devoted, of course, to describe the mini array. The other is about the core science, the one that we intend to do when the telescopes, all the telescopes, the 9 telescopes will be implemented, and will last 4 years. We have a source of observatory science, so in which people can propose something different. For both extragalactic and galactic observatory, you have also the IRF that you can download from Zenodo. Well, it's a so-called mini array, but in the end, it's not so mini, in the sense that they're not so small, in the sense that the telescope are 4 meters in diameter, but with a very large field of view. But the reciprocal distance is quite large, is about 200 meters from each other. And you see that here there are some of the main parameters. For example, the flux sensitivity in 50 hours of integration. In this case, you see that, of course, we have some advantage compared to the other already existing facilities, atmosphere, and also CTA for beyond, let's say, 10 TeV. We have a very good angular resolution of the sort of 3 arc-minute, but can be improved with some cuts in in the choice of the showers to something like 2 minutes. But what is very important in the field of view, you see, compared to magic, for example, is a huge. We are talking of an improvement of factor 2 and 3 compared to the current magic. But okay, as it was mentioned by Roberta, we would like to focus our research on the study of gamma ray sources at high energies. And we have small fluxes. So the best way to run the facility is to focus our observational time on a few sources very important to understand their nature and resolve and on. And so this is the reason why we would like to, we have this sensitivity with 200 and 500 hours, and we can try to compare our sensitivity to the astroparticle arrays like Oak or LASO. And so I'm not, I'm born as an X-ray astronomer, and we have a different way to compare the parameters, but I find always very difficult to compare the parameters between the atmospheric Cherenkov and the astroparticle array. Here is a synoptic table, and you see that, by the way, that ASTRI compared to the already existing arrays, atmospheric arrays, has a better field of view. Of course, it behaves pretty well beyond 1 TeV, but the angular resolution is also pretty good. But okay, I think it's useful to compare in the table with Oak and LASO, in which you see that the field of view is a huge. This is a big advantage of the astroparticle arrays. I mean, the astroparticle arrays are extremely efficient. Of course, they have to integrate, but in the end, it is natural to integrate over the time. But okay, what is lacking, at least at the moment, is the angular resolution. And here, I think systems like before CTO, of course, systems, 5 minutes, okay. I try to shrink it, can help a lot. Okay, what is the observing strategy? Well, once again, we have to deal with low flux sources because we are beyond 1 TeV. We aim to work up to 100 TeV or more. So the idea is to focus on a few fields with long integration time. We have the advantage of the large field of view. Thanks to the new kind of camera based on silicon PM, we can work also at the moonlight. So we have an increase again of 50–80%. And of course, we can work also with a larger zenithal angle to improve our sensitivity more. So here you see that this is a gaining that one may obtain with considering also the nights with moonlight with an increase of a factor up to 15 of the dark. And taking into account of this advantage, we can rely on about 2,000 hours per year, which means more or less 10 fields, not 10 sources, 10 fields observed for 200 hours, which is a huge, it's a lot. Why? What is the scientific aim? As I said, we wanted to help, I mean, we are in the era of the astroparticle arrays like Oak and LASO, but we know that problems of try to understand what is going on. And the angular resolution is too poor at the moment for the astroparticle array. And this was, so we have to help to identify the sources that are not yet recognized. So this is an example. So this is not approved, but it could be our plan of observation for the first 4 years. You see we have 2 pillars we wanted to study. One is on the origin of the cosmic rays, the other on the cosmology and fundamental physics. So we are more galactic sources to study, but are quite natural. And again, you see here the time that we would like to dedicate is a lot, but can be done. And I think this will be a good step forward because we will help to disentangle the origin of these sources. So let's take just 2 cases. Yesterday, we spent a lot of time in discussing Sinus OB2. We had more or less 4 or 5 talks with 4 or 5 different interpretations. Okay, I see Brian laughing, but this is the case. And in practice, we had also in the past similar situations when we have a lack of resolution, of a way to understanding, I think to the gamma ray burst, or if you want also to the crab before understanding the real configuration before Chandra. So it's a messy situation in a sense. And we performed a data challenge of the senior region, and of course, as expected, okay, here we consider just the point-like sources coming from the Oak catalog, and you see that we are very able with just 200 hours for the entire field, which is a huge, to have an important view of the main sources. But of course, we are also able to study diffuse emissions. Okay, I'm going to close much faster than Roberta, which was a disaster. And the same for the galactic center. In this case, we can take advantage from the fact that we can also make some high zenith angle observation, which would increase our sensitivity, and so our capability to understand what really is going on in the region where we're supposed to have a pevatron. So just I'm rushing to the end. The mini-array started as a concept of a standalone experiment in 2019 when we realized that it wasn't possible to implement it in the southern array of CTO. This is our president, Nicky D'Amico, with the Rafael Rebolo of the director of ISA, under signing the first agreement and visiting the site. This is myself a few years ago. You see the foundation, the first foundation that was digged. And you see this is the area where the telescope is being implemented. This is a strip of about 700 meters by 300. You see that apart from the telescope, many other structures have been already implemented. Okay, this is a picture of the first telescope that was brought to the top of the mountain and now has been installed. This is an example of the alignment of the mirrors. You see that with a procedure, software procedure, it's possible to start from this situation where all the petals are misaligned to this one. And what is interesting is the fact that this was done from Italy. So it was completely, the software allowed us to drive the telescope and the mirrors from Italy. These are the other telescopes, 8 telescopes are being produced. So you see that we are in a very advanced production. We have 2 companies working on that, IAI and Dalbin. The camera is very important. It's a camera with a particular hardware. We have the largest pixel of silicon PM pixel ever produced by Yamamoto specifically for our project. And we use a CT-ROC ASIC electronic with a peak detection technique, which has some advantages, including the fact that we have the production of just a reduced amount of data. So we don't need on-site data preprocessing, but we transfer everything in Italy every night. So this is already new. This is July, and just a couple of weeks ago, we have produced the first camera of the mini array. This is the garden of our observatory in Italy, and this is the old Zeiss telescope, and we performed some tests in the garden with a lot of light. It was a moonlight, but you see that it was a very good pulse shape definition, and these are real data. These are the muons doing Cherenkov on the filter of the camera, and these are real shower detected with just this, very simple collimator. So just this is this picture was done by a child who visited the site and produced this fantastic drawing. We are in the way of implementing the ASTRI mini array. We should have by June 2025 4 telescopes working with also the cameras, and the other will come, and we will start to make some science with these 4 telescopes. Of course, we are eager to collaborate. We are, of course, there are many people working in the different facility, but we can find a way to collaborate together. And this is a picture of the people working hard also in this moment for the mini array. Thank you.
We have time for questions. That's one hand there.
So will there be a symposium at IAU GA Rome 27?
Will there be a symposium at IAU GA 27?
I didn't catch the Yes, of course. Of course. This is the goal.
We have time for one more question.
Okay, so the point is to understand if a CTO will be ready for 2027, but this is a...
All right, let's thank Giovanni again. Okay, so the next talk is by Stefan Wagner, and he'll be talking about surveying the gamma ray sky with his. So, Stefan, that.
Down there. The fourth talk, the fourth PDF from the talk. Okay, so thanks very much for having me, and thanks also to Roberta for introducing the subject, so that saves a few minutes. I'm talking about surveying the gamma ray skies with HESS, and so just to sort of
illustrate that we are almost local. I just amended the logo of the symposium a little bit, so Hess is over here. You've seen images already, and you know what Hess is, so I actually skip over that very quickly. Just for those of you who are not familiar with the subject, so we are a hybrid 5-telescope array. The 5 telescopes collectively have more than 1,000 square meters of mirror area. The 4 medium-sized telescopes are operational since 2003. The large telescope in the middle is operational since 2012. Both subarrays have had their cameras upgraded. For the medium-sized telescopes, that was in 2017. For the large one, that was in 2019. We are operating under moderate moonlight condition, following the tracks of our colleagues at MAGIC who introduced this technique, but we are still a lot more conservative with our moonlight considerations, so we are a little bit more restricted. However, we actually operate for the past 5 years with more than 97% efficiency throughout, and that actually gives us more than 1,400 hours of dark night per year. So just in case you actually don't know what to do over the weekend, we are only 4 millilight second north of here, so that's 1,200 kilometers if you do the works, and that actually can be done in a single day, but it's a long drive. Nonetheless, so this is about surveys of the skies. The surveys of the skies is an obvious product of wide field instruments like the Water Cherenkov facilities, and you may wonder why I'm actually talking about a pointing IACT instrument at that special meeting over here. And the point is that Hess actually is a wide field instrument. So by all standards of our colleagues in any of the lower frequencies, with the field of view of 5 degrees, which is twice as large as that of any of the operational facilities. So Astra will of course beat us, but that's a few years to come. We can actually do quite a lot. A single exposure covers more than 20 square degrees. And for those of you who are actually working in other areas of the sky, so this is just comparing it to one of our larger sized sources. In the middle, you see actually a picture of Westerlund 1, a local star-forming cluster, which has a degree and a half across. So in comparison, you see that this nicely fits into the 5 degree field of view that we actually have, which is comparable to those of you actually a bit old-timers here to a Palomar survey Schmidt-Blatt. So this actually allows for images of very extended sources, and it does allow for surveys. And I think the one that's probably best known is the Hess Galactic Plane Survey, which was published a few years ago. These are just 4 of the panels over here, and you see there's a rich variety of sources. Actually, a large number of them are spatially extended, and you see all of them labeled over here, including the ones that are actually in the counterparts. So these are 2 more of the panels that I'm going to show you. The whole thing has been published, as I said, a few years back, and the results of the 2,700 hours worth of observing that went into the first galactic plane survey is a full coverage of the area between 250 degrees longitude all the way to 65-degree longitude. So that's what we can do from the southern hemisphere, including, of course, the area around the galactic center, and it's going to galactic latitudes of ±3 degrees. So it actually is rather confined, but as you do see in the images, and as you've seen in the ones that I just showed you, the TeV sources are actually fairly concentrated towards the galactic plane. This is all going down to to a variable level of significance, because the exposure is actually not homogeneous in the first galactic plane survey. The most shallow parts actually go down to a sensitivity of 1.5% of the Crab Nebula, and we do all of that at an angular resolution of 0.08 degrees, at which, as I said, the majority of sources is spatially extended. So in the first galactic plane survey, we found 78 sources, 11 of which are dark. That's to say they do not have an obvious counterpart in any of the other frequency bands. And while we are working hard at identifying them, there still is not a unique identification for those. Of course, by comparison, there are 67 sources with firm or at least very plausible associations in the catalog. But I need to say that 11 of those sources are very complex, multi-component, and it's quite plausible that if we actually look at that in a little bit more detail, it turns out that there are actually multiple sources, and the number of true astrophysical objects in the catalog might be larger than that. So closing up with the final 2 panels of the first galactic plane surveys, I would just like to reiterate that all the data are publicly available. So you're getting FITS maps of significances, fluxes, errors, upper limits, and the sensitivity to different correlation radii, which actually allows you to actually compare sources at different angular scales. And you can play with them. They're all publicly available, including the catalog, including the images, many of which are not part of the original paper. Jupyter notebooks to actually work with the data on your own, and I very much encourage you to do so. There's a fairly large number of papers in the meantime of colleagues who have actually used the data that we put out in the first galactic plane survey for other purposes than the ones that we originally published it on. Going on, there is another survey which some of you might have seen results of, which is the first inner galaxy survey that we conducted, and it's actually published in parts in First Rev Letters in 2022. This is the central area, 550 hours of high quality data. Latitude is more constrained, longitude is more constrained, plus or minus 5 degrees. Latitude goes from -3 to +6 over here. And what we did in this first paper, we published the dark matter limits that came out of this investigation. So this is one of the various limits that we actually published. There's been a question on that earlier on. And you see that with this explicit data set for very many possible channels, we're actually going down to the thermal relic limit of the dark matter constraints that we can come up with. There's of course also the opportunity to study this very good data set, this high quality data set now for sources. Those are in progress, and I'm hoping very much that you're going to see the results of that fairly soon out in the literature. There are more HESS surveys to come. So the one which actually is in the very last stages, and again, I'm pretty sure that you'll see that by the end of the year, is the first HESS extragalactic survey, which is actually combining all the pointings that were done with the array prior to the inclusion of the CT5 telescope in the middle. There's, of course, a HESS Galactic Plane Survey 2.0 that we're working on, where we will actually considerably improve on what's been done in the first HESS Galactic Plane Survey, both in terms of coverage and in terms of sensitivity and in terms of homogeneity. And so this is something where we actually hit now the limit where the distinction between sources and components gets more complicated. With the majority of the galactic sources being spatially extended, we are actually source confusion limited. So it's quite clear that at the level of the second HESS Galactic Plane Survey, it actually becomes very difficult on the galactic plane to find a blank patch of sky. So we actually are in the source confusion limit, and that actually tells you something that actually will need to be considered for the future surveys to come, that we actually enter this regime there. And I'd like to reiterate, that's not because the point spread function is bad by comparison. It is not as good as you find in the optical or the radio, but it's because all these sources are spatially extended. We will actually have a further HESS inner galaxy survey, which is both wider and deeper. And again, so that's something which we, of course, use not only for dark matter, but also for source considerations. There's a shallow, high latitude galactic survey exploring more of the skies there. And again, sort of another survey where parts of which have actually already been revealed is the HESS Large Magellanic Cloud survey. So it's just a few weeks back that we actually had one central piece of the Magellanic Cloud, which is part of this Large Magellanic Cloud survey being published. A few years ago, we actually published the original investigation of the Large Magellanic Cloud, and one of the sources there was this supernova remnant Pulsar nebula N157B in the middle over here. And while we already in the original publication understood and pointed out that this is not a point source, which is something that you would expect for a Pulsar nebula at the distance of the Magellanic Clouds, it's with this larger and more sensitive data set now that when you actually subtract the Pulsar nebula out of that, you start to see quite a number of other sources. And this particular paper over here is actually concentrating on the star-forming cluster R136, which is the most luminous star cluster in the Magellanic Cloud, and it's also a VHG source, and it's the most luminous star cluster by that definition, of course, in the local group that's known to be producing gamma rays. And I'd like to conclude with a survey which is a bit unusual, but I thought I'd sort of show that nonetheless. You can actually use all these observations to also conduct a survey of cosmic ray electrons, which is also something that we've done and which will hopefully be published in the next couple of weeks. And that is actually using data coming from all the observations that were compiled with the medium-sized telescope CT124. For that particular purpose, we left out CT5 because its field of view is a little smaller. We actually used, for homogeneity reasons, only the data taken with the first configuration, because for this kind of study, systematics actually really is a very crucial element. We actually went by our standard quality cuts, but we limited the data set further to sources or to areas where we are observing with a zenith angle of less than 45 degrees in order to maintain a homogeneous threshold in energy. We are only looking at the dark parts of the Milky Way, so to say, so we stay away from the galactic plane at least by 15 degrees, and we also stay away from the Large Magellanic and the Small Magellanic Cloud by 5 degrees. We only use the high quality showers coming from 5 telescope events in the central parts of the shower. Again, that's all for the sake of homogeneity. And we also stay away from any source that we find with a rim of at least a quarter of a degree. So what's left there in this study is actually a minute contribution or contamination by cosmic ray protons, which are very hard to distinguish, and a few gamma rays. And that you're left with all the cosmic ray electrons from those patches in the sky. We analyzed that and derived a spectrum for all of the cosmic rays over here. It can nicely be fit by a broken power law with all the various parameters that I won't go into and won't discuss at that particular point, other than to sort of leave you with the main message that the sharpness of the break that we see illustrates that it's extremely unlikely that the cosmic ray electrons come from a diffuse sea throughout the Milky Way. It's equally unlikely that the cosmic ray electrons come from a single source, such as, for instance, the Vela pulsar. It is much more probable that the cosmic ray electrons that we see comes from a rather small number, say 5, 6, 7 sources, that actually produce the majority of those cosmic ray electrons. That's being discussed in the paper that will be out in the literature very soon. And the interesting thing then, of course, is to go back and ask yourself, well, if it's only 4 or 6 or 5 sources, well, what can we do in terms of actually doing an old-size survey and localize the sources by a multiple consideration of the various patches that we actually have? That's also something which will come and which will allow us also to study that. I'd like to conclude with actually looking at what we can do for our survey properties. It does, of course, rely on very high reliability, so very high and homogeneous quality, which actually always limits the total data set that's available to any of those surveys, more so than a particular source study with some homogeneity is a bit less of an issue. It also relies on a high duty cycle, and as I said, with the 1,400 hours a year that we come, we are actually in a very good position to do so. It would actually allow HES to cover the 28,000 square degrees that's visible from the location in Namibia, down to a sensitivity of about 5% of the crab in just 2 years. Of course, you could limit it further to the area that's not being covered by the water Cherenko facilities or the facilities like Lasse and Hawk in the north. But that's in principle possible. Of course, it would actually not leave any time for time domain programs, which is a critical element in the HES science program. But it just illustrates the options as well as the limitations that you have with a pointed ICT. Now, I should point out, talking about time domains, we actually do conduct surveys more or less continuously in a different kind of domain because we actually follow up quite a large number also of the Fermi GBM gamma ray bursts, which have a poor localization. So you're getting the exquisite ones from Swift, but actually Fermi GBM, which is actually seeing a great many more gamma ray bursts, does have a poor localization. And many of them actually are not well enough localized to be put out with a pointed instrument. But we can actually carry out mini surveys and tile the area within a relatively small amount of time and cover 60 square degrees easily within a couple of hours after the gamma ray burst has shown up. And so that's something that we routinely do. And the same thing, of course, applies to the alerts coming from the gravitational wave interferometers, which, as you know, have a still larger index. Now, however, this is not our survey strategy. All the surveys that I mentioned combined actually take only 10% of that area, but of course they do go significantly deeper, and I encourage you to stay tuned. And since we are at the very end of the symposium, just in case you missed out the HEF booth that we have, it's being wrapped up. So if you rush after the session, you might still find a few of the posters that are hanging out there. And nonetheless, that we had a couple of displays telling you all about the observatory, all about the collaboration, about the various things that we can do, that you can do if you're not a member of the HES collaboration. There's quite a lot of that. And that is all actually on a dedicated web page that is actually for the specific symposium. And if you go to that one, you'll still get a lot of information about that particular site. And I close with my very last words. So we feel very much at home here, and that's leads to the fact that if you look closely, very close to our telescope here, there's something which is actually reminiscent for many of you, because the Table Mountain here is so very similar to the mountain that we actually have at the head side. It's the same height, it's the same flatness, if you wish. We even have something like your Signal Hill and other things. It's called the Little Gamsberg in Namibia. So we're very much at home, and it doesn't end there. If you look at our little inset here, this fantastic stadium, which some of you might have seen, is constructed by the same company that designed the Hess telescope. It's not a coincidence. These are the companies that do these sorts of things. And to very close you, if you actually brought the telescope along, it would stick out of the stadium, but if you turned it over, it would just fit perfectly inside. So with that, I close and take quick questions. Thank you.
All right, thank you. Unfortunately, we are running out of time. Still 2 more talks to go, and there may not be any coffee time left after this. So let me just take one quick question, just one sentence.
You mentioned the high galactic latitude survey. Up to what, how many degrees in B galactic latitude do you plan to cover?
I won't be able to give you the ultimate number because we are currently designing the legacy program for the next 3 years, and we'll see on what we will actually do in this regime. So stay tuned.
Okay, okay, thank you.
Indira Vergara here.
Hello, yes, I'm here. Can you hear me?
What a remote? I see only one remote. Okay. Okay. Sorry. Do you have to ask the speaker to move to the next session? Okay. All right. So the next talk will be remote by Indira Vergara, and it will be talk about latest results from the search for ultra high energy photons. Okay. You can go ahead.
Thank you. Good afternoon, everyone. I'm talking about the latest results from the searches for ultra-high energy photon at the Pierre-Auger Observatory. The Pierre-Auger Observatory is located in Argentina, and that we study the highest energy particles in the universe with energy about 10 to 16.5 EVs. This observatory uses a hybrid detection, which consists of an array of water Cherenkov detector spread over an area of 3,000 kilometers square. You can see in this scheme, the water Cherenkov detector is represented by the black circle and bordered by the Florence detector, whose field of view covers the atmosphere above the SD array. And here is a picture of one of the buildings of the SD. And in the Pierre-Auger also has a 3 high elevation Auger telescope. Here represented by the orange lines and cover the atmosphere of a small and denser area called infill. In this slide, there is an example of hybrid event, which is detected by 2 of the telescope of the SD. And with this information, we can build the profile, the longitudinal profile of the shower. And also this event triggered 24 stations of the SD And with that information, we can reconstruct the lateral profile of the shower. Here are some examples of the signal collected in the water Cherenkov detector. These signals have different characteristics depending on the nature of the primary. For this difference, here mentioned some of the difference. We obtain discriminating observables in order to separate photon from hadron primaries. The Auger prime is upgraded done in the Pierre Auger Observatory. Among them, there are the installation of scintillator on the top of the Warren-Cherenkov detector in all of the array. Other upgrade is the Amiga project that consists to install underground moon detectors that is scintillators around the Warren-Cherenkov detector, but this was only applied to the infill area. In these slides, there are 4 analyses corresponding to the search diffuse flux of photon in all of the range of energy that observatory Pierre Auger can be detected. For this analysis, use different observable depending of the detecting techniques that use. For example, for the lowest energy range, the observable used from the moon detector and use data collected by more than 4 years. And to set the data sample, we need to apply different quality cut to the data. And this graphics shows the value of the observable for data, and we can compare also the values obtained for photons and proton shower simulations. Also is presented this line which represents the photon selection cut. And for the analysis like this one, some photons even past this cut. The number of these events are congruent with the expected numbers for the background events. In all of this analysis, no significant excess have been found, and the final result for these cases are given in terms of the upper limit of the integral photon flux. Here is the result for this analysis, and also it's displayed in this plot. You can see that the upper limit provided by the Auger analysis are the most stringent limits over the wide energy range. And also we can compare with the photon flux calculated for different theoretical models. For the Auger results over the EEV energies, the upper limit obtained in the Auger are in the range expected by the G zeta k photon flux for 2 pure proton scenarios. And also we have these green bands that show the expected G zeta k photon flux, assuming a mixed composition that would be fit with the Auger data obtained from the analysis, the mass composition analysis. While this blue band represents the photon flux obtained from the cosmic ray interacts with the matter of the Milky Way. And also in this plot are shown different photon flux obtained from the decay of super heavy dark matter particles. And here is presented another analysis about search for photon from for pointing sources. And this is a blind search and is performed in the range of energy around the EEV and use hybrid data. And we use a range of declination band expressed in this mentioned here. And the selection of photon-like events is optimized from its direction. Here is an example of the pixelated area. And no evidence for an excess of photon-like events has been found. For that reason, it was calculated the flux upper limit for photons. And here is show that result as a function of the galactic coordinates in the celestial map and the celestial maps. The absence of detectable point source in this range of energy does not mean that the source of EV rays are extragalactic. There are another research about searching for photons, taking account a specific target. In this work, we analyze data with energy around to the EEV also, use hybrid data, and we select 12 target class that is listed in this table, and the first 10 ones correspond to the galactic sources, and the other 2 correspond to the extragalactic sources. In this case,
you have 3 minutes.
Okay, thank you. In this case, no target class revealed compelling evidence for photon emitting sources in this range of energy, and it also calculated the upper limit for photon flux. The other work is searching photons in associating with gravitational waves. In this case, evaluated events with energy above to 10 eV and use the events detected in the SD array. We use gravitational wave events observed by LIGO Virgo and were selected by close and well location, and only found 10 coincidences in 2 times windows. And also we could not find evidence of photons for these events and calculate the upper limit for the fluxes. Bueno, as a summary, I can say that the Auger results are the most stringent limit in the incoming ultra-high energy photon flux over 3 decades of energy. And also we have the first results for searching photons from the different events of gravitational wave. Another point is the Auger prime improve the discrimination between the electromagnetic and harmonic component of the air shower, and this could be provide a better observable and improve the capability of the Pierre Auger Observatory as a multi-messenger observatory in the near future. Thank you for your attention.
Thank you. All right, so we have time for a few questions. Is there any question online? Okay. I don't see any question. So the next speaker has agreed to present in the next session. There's an empty slot there. So that will bring close to this session. Yeah, thank you for attention and thanks all the speakers. So it's a coffee break now. Please come back at 3:30 for the next session.
Okay. I'm your chair. I think we're going to start because we should get to the closure. So we have first a contributed talk that is Davide Piccolo. He's going to talk online about RPC-based GRB Hunter.
Yes, can you hear me?
And if you can put your slides, Davide.
Yes. Just a moment. Okay, can you see the slides?
We can see your slides, great.
Okay, thanks a lot. So I will talk about the a proposal for a demonstrator for an RPC-based GRB Hunter. And on behalf of these people from the different institutes in Italy, from INFN and INAF. GRB have been discussed in the past sessions. Many of them have been detected with satellites experiments. Fermilab discovered more than 180 GRB, and 29 of these with the emission above 10 GeV. Anyway, due to the limited size of the detector on satellites, they cannot go at much higher energy than 100 GeV. If you want to explore higher energy, we have to build the experiment on ground. There are a YACT technology that has a good angular resolution and good and energy resolution, but with a lower duty cycle and lower field of view, and they identified 6 high energy GRB in TEVCAT, or with arrays of detector that have a lower good angular and energy resolution, but higher duty cycle and higher field of view. And the discovery, the detection of in 2022 by the LASO experiment of the GRB with more than 5,000 photons above 500 GeV is an example of the interesting possibilities. Detection of air shower on ground with air shower arrays can be done with the two different techniques. So one is the particle counting, in which is a small thin detector less than 1 radiation length can count the number of particles crossing the detector and make a signal proportional to the number of charged particles. As an example, plastic scintillators or resistive plate counters are used for this kind of technology, with a typical detection energy threshold in the order of a keV. The other approach is the calorimetric approach, in which a signal is proportional to the total incident energy of an electromagnetic particle, and they are using water Cherenkov with the tank of water and exploit the Cherenkov flight of the particle inside the water. But in order to have this, you need at least 1 MeV for the secondary particle in the water to trigger the Cherenkov light. So in this talk, I will consider the particle counting approach with the resistive plate chambers. So what is an RPC? An RPC is a thin detector, 2 millimeter wide gas gap with 2 millimeter electrodes, bakelite electrodes, at which we apply a high voltage. When a particle crosses the sensitive volume of gas, they ionize the gas, and then and under the action of the electric field, an avalanche is generated in the detector. We can pick up the signal from copper strips or pad put outside the detector. RPC usually operate in streamer mode or avalanche mode. We are now exploring the avalanche mode, in which exploring gas mixture with tetrafluoroethane, isobutane, and SF6. With the avalanche operation, we have a reduced charge inside the detector. This improves the linearity of the detector that can go up to count up 10 millions of particles per square meters. And also they require lower glass flow, that means less cost and also less maintenance. And also we can control better the crosstalk and the noise. RPC have been extensively used in high energy physics. 3 of the 4 LHC experiments at CERN use RPC for a total area of more than 7,000 square meters, and have been operated for several years with very good performance. You can see, for example, the stability of the efficiency and of working voltage for RPC used in the CMS experiment. So RPC have been demonstrated as a good detector with a reasonable cost, high detection efficiency in the order of 97%, and excellent time resolution in the order of 1 to nanoseconds. RPC have been also used for cosmic ray physics in the past. The Argo experiment in Yanbaijin in Tibet, where they built more than 6,000 square meters of RPC that were operated with very low maintenance between 2007 and 2012. They achieved an angular resolution of half a degree for 1 TeV particle and covered an energy range between 100 GeV and PeV. These are some pictures of the experiments and the layout of the carpet of RPC, segmented in chambers and pads or strips for the readout. In these slides, there are few performance of the RPC in the Argo experiment. In the plot on the top right, you see a real event in which the projection on XY projection is reported as a function of the time of arrival on the RPC carpet, and you can reconstruct the direction of the primary gamma looking at the time of the front of the shower. And on the bottom side, you see the performance in terms of angular resolution. In black, there is the profile of the mountains around the RPC carpet, and overlapped in red, there is the fraction of showers with theta above 80 degrees that have been reconstructed, and they very well match the profile of the mountains. And on the right, you can also see the moon shadow with the hairs above 60 degrees. One crucial point to identify gamma ray burst at lower energy is the triggering. In the RPC carpet has the characteristics to have a very low energy threshold for secondary detection, and also is a very silent detector. In Argo, for example, we had 380 Hertz per pad. Half of this was due to soil radioactivity, and so it is possible to build some trigger based on particle multiplicity. For example, in Argo, they used an inclusive trigger with a majority of 20 pads over 15,600 pads. That is a trigger almost accidental-free. And if you look at the energy distribution for different interval of pads, for example, between 20 and 39 or 40 to 59, for the interval number 1, with the lower number of pads, we have a median energy of the distribution of 340 GeV. And some fraction of events triggered also at 100 GeV and below. This is the official trigger that was used in Argo, but also some other triggers were studied by the Argo experiment, reducing the time window in which we make the coincidence of the pads, and trying to have a low multiplicity trigger with 10 pads over 15,000. And you can see that they could achieve an effective area of 200 square meters at 50 GeV. Here, the point is that we have some room to try to study smart trigger using the flexibility and granularity of the readout of the RPC. So RPC have been already presented in the past as a possible option for gamma ray physics, in particular in southern hemisphere. What is new now that after the pandemic crisis, there was a national recovery plan in Italy in which the INAF and INFN were get some budget to build an order of a 100 square meter system of an hybrid system done by RPC and water Cherenkov detector. So we already ordered the RPC for a total amount of 100 square meter, and we plan to build this detector and to test together with the water Cherenkov to study the synergy between these two technologies and make some tests at a high quote to understand if they could give some impact in this kind of physics. We asked to carry these activities inside the Zwigo collaboration, and so we proposed to build this small demonstrator and test with them for a possible future upgrade of the experiment in case. So we started some laboratory tests with small chamber, the small chamber done with the 6 strips on one side and 1 pad on the other side, and we get very good results in agreement with what we already know in terms of the efficiency, that we have a nice plateau at around 10 kilowatts, time resolution between 2 and 1 nanoseconds according to the voltage applied, and a reasonable charge that we can exploit to have also an analogic readout of the detector. We are also developing a front-end card to read the signal from the pad, and we have tested this to cross-check the time resolution that was less than 2 nanoseconds for this test, as already also without electronics. And now what we are trying to do is to optimize the full-size detector. We have a full-size detector in laboratories. It's about 3 meters times 80 centimeters, divided in 14 pads, each of 37 times 40 centimeters, divided in 2 rows. On each of these pads, we have a front-end board to take the signal, amplify this and discriminate and send to a concentrator card that distribute low voltage and send the readout signal to the DDRQ. And you can see some of the picture taken in laboratory with also the test that we do for the quality control of the chamber when they are produced. These are the first preliminary results taken in laboratory with this full-size chamber. Also, in this case, we have a nice plateau with a maximum efficiency that in this plot is limited by the geometrical acceptance of the trigger. But we confirmed the nice resolution in terms of time resolution of 2.2 nanoseconds at 9.9 kilovolts, also with this larger pad that could deteriorate a little bit the signal with respect to the strip that we usually use for this kind of the detector. So we are very satisfied of these first results with the full-size chamber. So what is very important when you want to use a gaseous detector for this kind of physics, when you go at a high quote, so with annual oscillations in terms of temperature and on the pressure, we are working at a lower pressure at around 600 millibar. So the Argo experience already shown that this fluctuation in temperature in Argo, there were fluctuation between -10 and 30 degrees outside, but the RPC were inside a hole, and the temperature variation were in the order of 10 degrees. But this variation of temperature and pressure are reflected in time resolution efficiency fluctuations during the different period of the year. Nevertheless, the stability of the angular resolution and of the pointing accuracy can be seen in the bottom plot on the left, that is very stable also if the temperature and pressure change during the time. Moreover, we got a lot of experience with the LHC experiment.
2 minutes. 2 minutes.
Yes, okay. We got a lot of experience with the LHC experiments, and now we can control the voltage of the system and modify it according to the temperature and pressure variation in order to have a very stable performance in terms of also of time resolution and efficiency. In any case, we are going to do some temperature cycle test and study at low pressure. Finally, we are planning to make an integration test with the Zwigo tank that our colleagues of the NFN Milan are developing for Zwigo. So we will go at the beginning of next year to put one big chamber on one tank and make a mechanical and DAQ integration test. And we are also going on with the RPC simulation. On the top of this slide, you see some performance obtained with the standalone system of RPC studied for the simulation in the past, but now we are going to integrate this simulation inside the Zwigo standard software. At the moment, these are very preliminary results in which the geometry of a big RPC has been integrated with a water Cherenkov tank, and we plan to have more results in the near future. So going to the conclusions, the low detection threshold of the RPC and the flexibility to merge information from a segmented readout of the RPC make this detector very useful to want GRB lowering the energy threshold down to 100 GeV and also less. At least the Argo experience already shown the possibility to have this good performance. Now we have this project to build a small demonstrator of the order of 100 square meters of RPC to be tested with an hybrid system with water Cherenkov detector tanks, and work is in progress to develop the chamber, to build the chamber, and going on with this R&D. And so we will try to develop this plan inside the Zwigo collaboration. So more results I hope that we can have in the near future, both in terms of simulation and of the hardware test. And that's all. Thank you.
Thank you. Have time for 1 or 2 questions, Krasmir? Then.
Thank you. Thank you for the presentation. I remember I was discussing several years ago at another conference in Rome with the colleagues, Italian colleagues, about these detectors, and then which were used in Argo. And then I asked the cost of such detectors, raised diplet chamber, and then I was told a 1 meter square cost was between 10,000 and 15,000 euros. I would like to ask if there is any change in this cost estimate per meter square of the detector.
It seems to me a little bit high cost. These, for example, for these 3 meters times 1 meter, so 3 meters, 3 square meters of chamber, it was less than 10,000. And in any case, we are trying. Some of the cost is also due to the soldering of all the strips. So going, for example, to pads, this reduce the number of soldering that you have to do. So we are trying to find some solutions in order to reduce the cost. And of course, if an hypothetic project would build more chamber, of course, the cost will go down. But in any case, the number that you have mentioned for me is a little bit higher than what we have experienced.
Thank you.
Hi, thanks for the nice talk. I'm wondering, I don't know too much about that kind of techniques you are using here, but is it possible to do offline analysis, for example, a boat like GRB after the trigger is happening? So what is your data collecting policy and the data storing policy? Can you do offline repositioning of the wall detector, let's say after a day or so? Or do you collect only the triggered data and store that data from the detector?
In principle, after a trigger, you just collect and all the pads that have signals and the time, the arrival time. So you have the collection of this with the position and time, and you can do, of course, offline analysis of this. The only thing you have to trigger the events, and at least in the Argo experiment, they use this majority trigger, majority of 20 pads. So if you have at least 20 pads in the full detector, you collect all the information from the detector. And you can do offline analysis, of course.
Okay, thank you. And we thank David again.
Thank you.
Next, we have invited talk by Ion Viana, who's going to tell us about dark matter and fundamental physics.
Okay. Laser. All right, so hi everyone. So I'm Ion Viana. I'm a professor at Institute of Physics of São Carlos in the University of São Paulo. And I would like to thank the organizers for inviting me to give this talk here. And I'll be talking about fundamental physics phenomena and how we can study them with astroparticle physics with these detectors, ground-based gamma-ray telescopes. Now, I'm not going to go into the details on the telescopes. The only important thing that I would like to highlight here is that we are focusing on very high energy gamma rays or ultra high energy gamma rays, so TeV to PV energies, which is the domain of imaging atmospheric Cherenkov telescopes or extensive air shower particle detectors. So what exactly do we mean by fundamental physics? So if we look typically at the TeV, PV particle and cosmology landscape, I think I can illustrate more or less what we mean by that by showing you this Livingston plot, which is an evolution of the colliders for the past, in the past and in the future. You have the LHC here, the high luminosity LHC here, and future proposals of the FCC, etc. And if you have a look here, even the maximum for the next decades, so even in the future, in the next decades, the maximum energy that we can hope to probe with the colliders to study matter and particles, it doesn't go beyond 100 TeV. If you also look at the history of the universe, so cosmology, when we talk about TeV, PV particles, we are basically talking about this region here, which is between 10 to minus 30 seconds and 10 to minus 10 seconds. So it's basically when the universe had 10 to minus 20 seconds. So we are studying phenomena that happened when the universe had only 10 to minus 20 seconds. So if we look at where did this happen in terms of history of the Big Bang, that's basically right after the end of inflation throughout what we known as the electroweak epoch, roughly around the period when the strong interaction becomes distinct from the electroweak interaction. So by studying astroparticle and very high energy TeV to PV energies, we are basically probing interaction between particles of when the universe had this energy, this temperature, and we are studying way beyond what accelerators are capable of studying. Now, there are several questions that we can try to answer with gamma rays, very high energy and ultra high energy gamma rays. We heard a lot about the other parts, like relativistic cosmic particles, the origin of cosmic rays, how they propagate, etc. We heard lots of very interesting talks in the past few days. How to probe extreme environments like neutron stars and black holes, etc. But we also can study the frontiers of physics then with these astroparticle telescopes. And that's exactly what this talk is about. It's about dark matter, how we can detect dark matter and study its nature, its particle nature, to study whether we have quantum gravitational effects on photon propagation in the universe, if we have axion-like particles, if they do exist. And that's exactly what I'm going to talk about. I'm going to talk in the opposite order of these questions here. I'll start by talking about axion-like particles. I will not go too much into the models and particle physics behind these models. I will try to focus more on the type of phenomenology and signatures that we can actually study with gamma ray telescopes. So axions, not axion-like particles, are pseudo-scalar particles. They are actually subproduct of the Pei-Quinn solution of the strong CP problem, meaning we don't know exactly why CP is not broken in the QCD, in the quantum chromodynamics. It should be broken spontaneously. It's not. So there is a solution that is to propose a new particle, which is the axion. Pseudo-scalar particle, for those who know what that means. If we take similar particles to these pseudo-scalar particles, which do not necessarily solve this problem, but they can exist in these models, and these are what we usually call as axion-like particles. It means that mass and coupling are not necessarily related. They can be any mass or couplings. And the interesting thing is that some axion-like particles, then they actually provide a good particle, a good candidate for cold dark matter in the universe. And when we study the particle physics interaction of these type of particles, another very interesting phenomenological aspect of these particles is that they can actually interact with photons. And they can convert into photons and vice versa in the universe close to a magnetic field. So you can have these two interactions that can happen, the Primakov effect or decay of axion. So if you have an axion, it can convert into a photon and vice versa. A photon can convert into an axion. And this can actually generate lots of very interesting signatures in the spectrum of gamma ray sources. that come from oscillations when these photons or axions cross magnetic fields. This is what happens. This is for one set of parameters. So a magnetic field of a microgauss, when a particle crosses inside the galaxy, so within 100 kiloparsecs, and these are the parameters, the coupling and mass of the axion-like particle, and this is the probability of oscillation, of conversion between axion and photons. So you can see that this happens exactly at this region here of around 100 GeV or 1 TeV and things like that. So you can see that in this region, you actually have a probability almost equals to 1 to actually convert within this length. And you have small oscillations here. So if you have this probability of half or 1, you actually will oscillate several times. So this will have several impacts. And one of the interesting aspects of or signatures that we can actually have with these ALPs comes in the when we study source opacity in the universe. For example, if you have this AGN, we heard a few times in the last talks, which is very far away, through the path of this photon, it will interact with the extragalactic background light, and it will most likely, there is a known null probability to convert into a pair of electron and positrons. So if you have an emitted spectrum here, the observed spectrum will be dependent on the distance here. So you have absorption of photons in the way. That's what we call EBL absorption or opacity. So this is a well-known effect. So when you add the possibility that photons can convert into axions, one possibility is that if you have a photon that within the galaxy where it comes, it converts into an axion. This axion can travel all the way to our galaxy and reconvert later. And by this, you will actually recover some of the photons that otherwise would have been absorbed by the EBL. So this is what you have. You have a photon flux, for example. It will convert into a ALP. So you have the flux of ALP as function of the distance that will increase and decrease later because it will reconvert into photons, and then you will have photons over the distance that will appear later in your telescope. Now, so you can have several signatures. One of the signatures that have been studied is with ground-based telescopes is that if you observe the diffuse gamma ray emission, you can, for example, try to look for an extra diffuse component in the gamma ray spectrum from, for example, star-forming galaxies. This was done, and this is what you have. For example, if the purple line is when you don't have any ALP, any axions. This is data from Tibet air shower, and this is from HAWK, the diffuse emission. So you can explain with different components, and then you can add a component that comes from ALP, from axion-like particles. So then you can study this new component, see if it has a likelihood of detecting it, and if you don't detect, you can constrain this new component. Another thing that you can study is by observing specific sources such as AGNs, blazars, etc. And this is a study also that was done by looking at several blazars, by fitting the blazars at low energies using MAGIC or Veritas or HES. And then you have on orange here without ALP conversion. And then if you add an ALP axion-like particles, you actually have this recover of very high energy gamma rays. So you can actually look for these very high energy gamma rays. And you can constrain these models, for example, by using upper limits from HAWK telescope or any other telescope. So this is the type of limits that you can have, like we didn't see any signs of axion-like particles yet. And then you can constrain in this plot where you have the coupling here, axion photon coupling versus the mass. And the limits are very similar between these two methods here, the orange or the blue. And you can compare it with other probes. You have lots, tens and hundreds of different techniques to detect axion-like particles, haloscopes, tabletop experiments with magnets, etc. So it's a very rich field, and we can actually provide very complementary limits for a specific region of the parameter scale. And we expect that with new observatories such as LASSO, CTA, and SWJO will actually improve these limits hopefully to reach what is called the ALP dark matter line here, which is not yet probed by many experiments. Now, let's talk about Lorentz invariance violation. This is also a phenomena that arises in lots of quantum gravity theories. Once you study in depth a lot of these new quantum gravity theories, lots of them will actually cause violation of Lorentz invariance, and this will have several consequences. One of them is that the speed of light in vacuum will actually be dependent on the energy of the photon. So you will have a differential speed of light. And you can also have modification on the photon interaction, cross-section, thresholds, etc. So in order to do a model-independent analysis of a Lorentz invariance violation, normally what we do is that we expand this violation terms into a Taylor series, and then we study the different modes here, the first order, second order, etc., where the EQG here is the Planck mass. So you're trying to study these phenomena close to the Planck mass. Now, there are several signatures that you can try to study with gamma rays. You can try to look at time lag between photons of different energies coming from a source. If they had left at the same time, they will arrive at different times. You can look at the change in the pair production and the gamma ray horizon. So you will actually have less absorption in the middle of the way. And there's a third type of phenomena is that you actually open the possibility that the photon can decay while it's propagating into pair of electrons and positrons above a certain energy threshold. I'll go through very quickly on these three types of signatures. So the gamma ray horizon, if you study how the EBL absorption happens, you can actually write in terms of the optical depth here. You have a term which is the expansion of the universe. Then you have a term here which is the threshold, the number of photons that you have on the way, and the threshold for pair creation. Then here you also have the center of mass energy and cross-section of interaction. If you add a term of Lorentz invariance violation, what happens is that you change the threshold for the pair production to happen, and you also change the center of mass energy for the interaction. So this will actually, one thing that I didn't mention before is that on those terms here, if you notice there's a plus and a minus. So it means that this invariance break, the violation can be either superluminal or subluminal. So you can either change either way. It depends on the model. So in the case of subluminal case, it will actually cause an excess of transparency of gamma ray sources. So again, you're gonna gain an extra component at high energies that shouldn't be there otherwise. For the time of flight studies, that's very basic. So you have a term here that will be caused by different terms of the Lorentz invariance violation, and you have the distance that it propagates. At first order, this is typically of the order of 10 seconds per TeV per gigaparsecs, and you can actually study with lots of different sources such as GRBs. GRBs are interesting because you have very short duration emission. So you can actually look for a shift in the arrival of low energy photons and high energy photons, and you can constrain with this. You can use AGNs, which are also variable. You can try to assume that they happen at the same time, all the different energy components. And you have pulsars that, although they are not very far away, because they are very precise, you can actually try to constrain their pulses, and you can actually have very good constraints on the second order term here. And finally, you have the photon decay. That's very simple. A photon can decay in Lorentz invariance violation scenarios above a certain energy that is typically given by this very simple formula here. And it means that if you take, for example, a photon of 100 TeV, it will have a mean free path that will depend on some parameters. It depends a little bit on the model. But if you notice here, it's much less than a parsec. So it means that if you detect a photon of 100 TeV, which we did, you can actually constrain a lot of these Lorentz invariance violation scenarios. So I'm not going to go into the detail on how these things are done specifically, but you do have this compilation, this very nice compilation in 2020 of all the different constraints that you can have on the first order for the superluminal and subluminal case, and second order, well, again, for different types of techniques. So you can have photon splitting. I didn't mention that, but a photon can also split into 3 photons with Lorentz invariance violation. You have photon decay, energy-dependent time delay, etc. Suppression of ash showers, I didn't mention, but that's also another phenomena that people study, that you can actually have a different evolution of the ash shower in the atmosphere if you also change this dispersion relation. That's quite obvious. And here I give you a few of references of studies that were done with gamma rays, with ground-based gamma ray telescopes such as HAWK, SWGO. We did a few studies in our group there by Umberto. He was a postdoc in our group, with Pierre Roger, and also with CTA. There are several studies that were done trying to study these Lorentz invariance violation scenarios. Finally, let me talk about dark matter. If you come from the astronomy side of this assembly, you probably heard a lot about gravitational effects of dark matter. You know that there is this problem of dark matter. And if you try to understand dark matter in terms of a particle, you actually can have a particle that typically will have a mass of around GeV to TeV, the standard model of dark matter. And these particles can annihilate and decay into standard model particles. So that's the idea behind studying dark matter with gamma rays. In these, what we call typically the weakly interacting massive particles, these particles that can explain the relic density of dark matter that we detect today with the cosmological probes. These necessarily need to self-annihilate to create standard model particles. And even if that happened in the past, it does still happen today. And it should happen if the dark matter particle model is a WIMP, it's a weakly interacting massive particle, it will self-annihilate in very dense environments of the universe, which is the case in the center of galaxies. Now, the self-annihilation rate will be proportional to the cross-section of annihilation, the density squared, and the mass, inversely proportional to the square of the mass. It will self-annihilate through some type of process that we don't really know. It depends on the model, and it will produce primary channels, which are standard model particles. These will hadronize or decay and produce final states, photons, electrons, charged cosmic rays, basically. So these charged cosmic rays, if they are produced after annihilation, they will diffuse if propagate in the galaxy, the magnetic field of the galaxy. They will lose directionality, but you can still study spectral signatures. You can look for anomalies in the spectrum of cosmic rays. That's what AMS does, for example, and it had found an anomaly in the positron excess there, which can potentially be explained by dark matter. And then we can also produce these neutral particles, photons or neutrinos. They have the advantage that they are not deviated in their trajectory, and they will point directly to the source. So you can do both. You can do spectral and spatial signature of an expected gamma ray signal. If you want to convert this rate into a flux, you have to introduce the spectrum, the number of particles that are produced in the final state here. They are typically a continuum with a cutoff at the energy of the dark matter particle mass. Then you can also have some electroweak effects close to the dark matter particle mass, which will generate in certain scenarios a line or a bump close to the dark matter particle mass. And then you also have to integrate this density squared over the line of sight. So you need to know how dark matter is distributed in the universe. So you need to have some models of dark matter halos. That's why we very often collaborate with astronomers that do galactic dynamics and try to give us halo models of different dwarf galaxies, the Milky Way, etc. Usually, we go and look for different models, either from numerical simulations or from direct observation of galaxy dynamics. The problem is that they usually give us different types of profiles, either very cuspy profiles or chord profiles. These are examples of the halo models of the Milky Way. Here you can see that you have a discrepancy, especially close to the center, of several orders of magnitude. And if you go to the square density, you have even larger discrepancies when you go to the center. So usually there's no way around it. In the galactic center, for example, the potential, the gravitational potential is dominated by the bulge anyway, so it's not dominated by dark matter. So that's why there is a trade-off between galactic center and dwarf galaxies, where you actually are dominated by the dark matter. So usually what we do is that we assume different profiles for the targets that we are looking at, and we use the different profiles as a systematical uncertainty on our expected signal. Now, there are several targets where we can look at. We have the galactic center, which is located very close to us. It has actually the highest expected dark matter annihilation signal in our sky. But the problem in the galactic center is that it has a very high astrophysical background in gamma rays. It's full of non-thermal emission. We have dwarf galaxies, many of them located within 100 kiloparsecs from us. They're extremely dark matter dominated, and they have a potential low astrophysical background. Then we have galactic galaxy clusters. They also have a very high dark matter annihilation luminosity. They might have substructures that contribute to the dark matter flux, but some of them also have very high astrophysical background in gamma rays. Then we have a local group of galaxies such as Andromeda. They are also relatively close, have a very large dark matter mass, and there are some studies showing that secondary emission might be important there. Let me start by showing you some recent results on dwarf galaxies. These are very robust targets. They are the most dark matter dominated system in the universe. These are the classical dwarf galaxies that were observed by Fermi and IACTs. Then we have new dwarf galaxies that were discovered by the Dark Energy Survey. And very recently, a study was done by all the different gamma ray observatories that took data on dwarf galaxies, Fermi-LAT, HAWK, HESS, MAGIC, Veritas, and they joined all the data that they have. They shared all the likelihoods that they had. And since none of them detected any gamma ray signal there, we can actually do a joint likelihood analysis and provide limits on the free parameter space of dark matter, cross-section, and dark matter particle mass. And this is what we get. So you combine, the limits are up to 3 times more constraining than if you had individual telescopes. So that's actually something very interesting that we can do with several different observatories when you combine lots of different things. They use 3 channels, so BB bar, W plus, W minus, tau plus, tau minus, J factor, so the distributions from this Geiger sum-math. The interpretation of these results are basically that below 2 to 30 TeV, dark matter limits are largely dominated by Fermi-LAT because it can observe a lot of dwarf galaxies. And above 2 to 30 TeV, depends on the channel, then IACTs and HAWK take over. So they are pretty much complementary in this sense. Now, one interesting aspect of dwarf galaxies is that we do have lots of new surveys of dwarf galaxies ongoing. Recently, more than 33 new ultra-faint Milky Way satellites were discovered. We have the Rubin Observatory that it's supposed to observe all the dwarf galaxies up to the Vireo radius. And a very interesting aspect of wide field of view observatories is that we can use legacy data from all these observatories to look at locations where new dwarf galaxies may be discovered, and we can keep doing analysis of dwarf galaxies to look for a potential dark matter signal there. So this is an example of the expectation of SWGO, the blue here. So we have an improvement of a factor of almost 10 in the TeV range. And here is a study that was done, if we assume that we have many more dwarf galaxies that are discovered with Fermi-LAT, we also get a factor of 3 to 5 improved limits there. Let me finish by just mentioning some results on the galactic center. So there are several studies that were done. So the galactic center can basically only be observed by southern observatories. So we did a study using HES, CTA, and SWGO. And by comparison, there was a study done by LHASO, but LHASO can't see the center. So they did a study located at 30 degrees and 45 degrees. They can study not the center, but still the halo. And we have to exclude this this region here because we have a very strong expected gamma ray signal there from astrophysical sources. And what we do is that we actually slice all these different regions, and we do this 2D likelihood analysis where you use both the spectrum and spatial distribution to separate the background from signal. We use an ANASTO profile, whereas LHASO uses an NFW profile. This is just a detail for these regions, faraway regions. It doesn't really make that much of a difference. And we use these profiles because it's very easy to separate a signal from a background if we have a CASP profile. But we also studied the effect of using a chord profile there. Now, this is the type of limits that we can get. This is combining lots of different experiments. So here's Fermi in blue. We have the HES limits here in green. We have CTA in red, and we have SWGO here in gray. Basically, we are sensitive to exclude or detect all different dark matter particles above these lines. So here's the thermal relic cross-section. This is the cross-section that we expect from cosmological models. And the take-home message here is that with these future telescopes, we'll be able to probe all dark matter particles with masses below 100 TeV, combining all these experiments below the thermal relic cross-section. So we either will exclude the standard model of dark matter, or the WIMP scenario, or we're going to detect something. We expect to detect something there. But this is for the BB and W plus W minus channel, just for the sake of completeness. They also have slightly different limits, but a disclaimer is that all this with SWGO was done using the strawman design, which is a outdated now design. We have a new array with much better sensitivity, so we hope to update these limits very soon. And one last aspect that is very interesting is a complementarity between SWGO and CTA. Here's for different dark matter particle masses. If we have this expected signal and compared to the sensitivity of SWGO and CTA, we can see that if we detect something, we can actually do complementarity studies between CTA that would be able to observe the continuum of the spectrum, and SWGO would be able to observe the cutoff of the spectrum. Well, I will skip this part. We have the decay of dark matter. That's also something interesting. Dark matter may decay. There's a very simple change that now you have, instead of cross-section, you have a decaying, and it's not proportional to the square, it's the density. But the study is very similar, and this is the type of limits that we can get with SWGO. LHASO here, there's a study that they did. It's also very competitive. But this exclusion here goes to the bottom, so you are sensitive to different decay types. Finally, things that I didn't mention, just to finalize, there are possibilities of different targets. I didn't mention irregular dwarf galaxies, galaxy clusters, Andromeda galaxy. I have the papers here for you. We have the possibility of decaying inside Jupiter or the sun, which is something that particle detectors can actually probe. Because we can observe the sun. We can't observe with Cherenkov telescopes, though, otherwise it would burn the camera. And we can also observe different types of interactions of dark matter. I leave you with all these references here if you're interested. And that's it. Thank you.
Okay, questions?
Regarding the Lorentz invariance violation and the time lag between the photons, you mentioned something around 10 seconds per TeV. Is there any current technology that is able to measure this time lag between different range of energy? And if not, what is the expected the CTA to observe this, for example?
Yeah, so it's 10 seconds per TeV per gigaparsec. So the further away the source is, the larger is the delay, the time delay. So that's why normally these type of studies are done with AGNs, which are located much further away, like with high redshift. So usually, I think I remember for PKS 2155, there was a study. I think the time delay they look for is at the order of minute or hours. So it's actually possible to do these type of studies. 10 seconds, it's quite small. We don't have, we do have sensitivity for 10 seconds. The problem is that we don't have statistics for 10 seconds, right? In a window of 10 seconds, we barely have one photon or something.
Okay, more questions? I have just one. For the ALPs, when you have the photon, it converts, and then the LLP converts back. Don't you change the direction enough just to still miss the signal?
Not necessarily, no, because if your photon comes and you convert into action, it will keep the directionality because it's a conversion, so it keeps the momentum. It's not.
Okay,
Really,
it's one to one.
Yeah, it's not a scattering. It's a conversion, really. So.
Okay, thank you. One more question. Okay, we thank Ion again. Thank you very much for the nice review. The next talk is online. Nikolai Budnev about the Taiga 1. And he should be on the Zoom. So it's up to Nikolai to share the screen. His screen.
Moment.
Okay, he's here on my Zoom. But...
Yeah.
Oh, great.
Do you see my presentation?
No, we can see you.
Do you see my presentation?
Yeah, now we can see your presentation. Go ahead.
No.
Yes, we can see your presentation.
Okay. Thank you. In the talk, I will present Taiga facility. It is an advanced hybrid detector complex for ultra-high energy gamma astronomy and cosmic ray physics. It is located in East Siberia, 50 kilometers from the south, the tip of Lake Baikal. The main goal of the Taiga project is to find a cost-effective way to create a large-scale installation for ultra-high energy gamma astronomy by combining wide-angle Cherenkov detectors with several relatively cheap, small-sized imaging atmospheric Cherenkov telescopes. As Taiga background, we used Razmik Mirzayan's experience in creating of imaging telescopes and our experience of
constructing of wide-angle timing Tunka 133 installation. The array consists of 175 wide-angle Cherenkov detectors distributed over an area of 3 square kilometers. Here is a list of Taiga collaboration members. German organizations have made a great contribution to the project. Unfortunately, their participation is currently frozen. The Taiga scientific program includes studies of high-energy gamma radiation from a large number of galactic sources, long-term monitoring and study of bright blazars energy spectrum, search for diffuse gamma rays with energy above 100 TeV, and other topics. This slide shows the location of Cherenkov detectors of Taiga-1 complex. 3 atmospheric Cherenkov telescopes are installed between 120 wide-angle Taiga high-score optical station. The distances between telescopes are 3, 4, and 500 meters. The high-score Cherenkov station distributed on area 1.1 square kilometers with spacing 106 meters. Each station includes 4 8-inch PMTs equipped with a segmented Winston cone. The resulting total light collection area of a station is 0.5 square meters. Threshold of array for cosmic ray detection is 100 TeV, and for gamma 50 TeV. We use various methods to synchronize optical station, including detection of light of lidars on a board of satellites. The IMS 1.1 nanosecond for time measurements ensures the accuracy of restoring the arrival direction of a shower about 0.1 degree. This figure shows the cosmic ray energy spectrum according to the data of the Tunka wide-angle installations. And this one is the mean mass composition obtained from X-mass. It is impossible to select gamma-initiated showers from hadron background using data of Taiga high-score only. But we can search excess of events number from the sum direction. This plot shows results of search of gamma with the energy more than 200 TeV in the direction of Cygnus Cockon in October 2020. The imaging telescopes of Taiga-1 array have a composite reflector of a Davis-Cotton design consisting of 34 mirrors with diameter 60 centimeters. The reflectors have a total diameter of 4.3 meters. Its focal length is 4.75 meters. There are the 600 PMT in the telescope's cameras. All PMT are equipped with Winston cone. The camera's field of view is 9.6 degrees. There are 4 ways to for detection of gamma rays in the Taiga experiment. First one, standalone mode of telescope operation. The second, stereoscopic approach. The third, joint operation of Taiga high-score and telescopes. And the fourth, with Taiga's high-score. In this case, additional suppression is required using, for example, data of muon detectors. This plot shows a histogram of background subtracted theta square distribution for 150 hours of crab observation in mono mode. And this the same distribution in stereo mode. And this slide shows the energy spectrum of the crab obtained from stereo mode data. It includes 12 events with energy above 100 PV. And this energy spectrum of crab shows our first hybrid data at energies greater than 100 PV. And at this picture, you can see energy spectrum of gamma from Blazar-Markarian 421 measured in mono mode. There are a lot of reasons to have particle detectors in Taiga complex. Our first array, Tunka Grande, consists of 19 installation station with surface and the ground parts. In surface part of each station, there are 12 former Cascada Grande installation counters, and in the underground part, 8 with same counters. Here, the Tunka Grande cosmic ray energy spectrum is shown. Here is the upper limit on the flux of diffuse ultra-high energy gamma ray according to the Tunka Grande installation. The criterion for selection candidates for gamma-induced shower is the number of all detected muons in all underground counters located at distance more than 70 meters from shower exists. To increase the area of particle detectors, new scintillation counters with an area 1 square meter of Taiga muon installation have been developed. Our plan for 2-3 years is to deploy 2 more imaging telescopes in these positions. Then effective area for detection gamma rays with energy greater than 100 PV will approach to 1 square kilometers. As well, in near future, we intend to install some Taiga high score optical station, then effective area of the array will increase up to the 2 square kilometers. As well, we intend to deploy at least 400 square meters of new scintillation muons detectors and experimental underground water Cherenkov detector with an area of 40 square meters. Here is a sketch of this underwater detector. In next further, using the experience gained during the creation of Taiga 1 complex, we plan to begin deploy the Tunka 100 installation with a hybrid detector system on an area of up to 100 square kilometers to advance into the PEF gamma astronomy. The Taiga 100 will detect about 350 gamma quanta from crab with energy more than 500 TeV for 300 hours of observation. And the experience of the first years of operation of Taiga 1 confirmed the effectiveness of hybrid approach to create an installation with an area of many tens of square kilometers for ultra-high gamma astronomy. our near future plan to a new 4-meter class and one 6-meter class imaging telescope, new particle detectors, scintillation and the ground change of water. And next plan, up to 100 square kilometer taiga array with 3,000 wide angle Cherenkov detectors, up to 10 imaging telescopes and 3,000 underground water Cherenkov detectors with area 40 square meters each. Thank you for your attention. Welcome to Siberia.
Thank you very much. Okay, we have time for a couple of questions. Ulises.
Hi, Nikolai, for your talk. I have a question concerning the site for the kilometer square array. So does the current site of Taiga, can it be expanded? Can it host a larger array, or you would have to look for another site? And can you remember me also what's the altitude where you are?
Yes, we look for another site for big installation. And now we look for two sites, one at height 1,000 meters and second about 2,000 meters. And all sites are in Siberia, not far from Irkutsk.
Thank you.
From Lake Baikal.
Thank you very much.
One more question? Online questions? Okay. We thank Nikolai again. Thank you.
Thank you.
And now we have Seikato, who's going to tell us about alpaca. I think it's also an online talk. Oh, yes, it is.
Can you hear me? Can you hear me? Hi, can you hear me?
Yes, we can hear you.
Okay. I'm going to share my slide.
Perfect. And yeah, we can see your slides.
I'm sorry, this is... Okay.
Okay. You can go ahead.
Okay, thank you very much. And hello, everybody. My name is Kato Sei from Japan. And today I'm going to talk about the current status of our project Alpaca in Bolivia to explore sub-BV gamma ray astronomy in the southern sky. And during these 2 days, we have many good presentations regarding the search for pevatons by means of sub-BV gamma ray astronomy. Actually, this field of astronomy has been pioneered first by Tibetan Gamma for the detection of the Crab Nebula in the sub-BV energy range, subsequently followed by the Hawk and Lasso. And these observatories are working in the northern hemisphere provides us so many good data which elucidate the supernova remnant G10-6, Cygnus cocoon, and so many enigmatic gamma ray sources, and also the detection of the galactic diffuse gamma rays in the sub-BV range. But missing piece is the observation of the southern sky. This figure shows the Fermi-Lat GB all-sky map, and I put here the equatorial plane to separate the sky regions accessible from the northern hemisphere and the southern hemisphere. The northern sky is good because we have access to the sky region with currently operating a working sub-BV gamma ray observatory. On the other hand, we don't have any access to the southern sky, but while the Hess galactic planes have discovered so many TV gamma ray sources in this southern sky region. In particular, we have many promising galactic pevatron candidates, including the galactic center which hosts a supermassive black hole, and Western 1, young massive stellar cluster, and HJ1702-4220A, which is very enigmatic gamma ray source, lacking likely counterpart for its sub-BB gamma emission. So the current situation requires us to construct the observatories in the southern hemisphere to get access to the southern sky. That's why we are advancing with the Alpaca project. The Alpaca collaboration is an international collaboration between Japan, Bolivia, and Mexico, and currently about 50 people are involved in the project. The Alpaca site is situated in Bolivia, and in the right map, we can see the cosmic observatory of the Universidad Mayor de San Andres. And near this cosmic observatory, we have a plateau site. We have selected this plateau site as the Alpaca site. And this plateau site is about 2 hours by car from the central city La Paz of Bolivia. And Alpaca makes use of the traditional detection principle of cosmic rays and gamma rays using air shower array technique. The first component is a surface air shower array covering a geometrical area of 83,000 square meters. And it's composed of about 400 plastic scintillator detectors. And these detectors are used to reconstruct energies and arrival directions of primary cosmic rays and gamma rays. And another important detector component is an underground muon detector array covering an area of 3,600 square meters. And this MG array is situated 2 meters soil overburden, and it's used to discriminate primary gamma rays and cosmic ray events by counting the number of muons in the showers. And in fact, we have already studied the data taking using with a mini prototype array called Alpakita in 2022. The figure shows the position, encloses the array of the Alpakita with solid black lines, and it makes use of about 100 scintillation detectors. And currently we are adopting an air shower trigger condition of any 4 detectors detecting more than 0.7 particles within 600 nanosecond time window, which results in an air shower trigger rate of about 300 Hertz. And I'm going to present it later, but let me say here, we are going to construct a southwest muon detector in this year to start the observation sensitive to gamma rays in its prototype phase. This is a timetable of the construction of the surface area of Alpakita. We deployed the detector in 2022 June, and in the same year, September, we have started the data taking with a partially completed surface shower array. But in the next year's April, we have started the data taking with the full completed surface array of the Alpakita. And this full array is currently steadily operating. The right picture shows one of the detectors we are using for the surface shower array. It has 1 square meter plastic scintillator, and the lead plate with 5 millimeter thickness is on it. And these detector components are contained in an inverse pyramid-shaped stainless steel box, which is used to reflect the scintillation light produced in the plastic scintillator by air shower particles. These signals are finally corrected by the 2-inch PMT installed at the bottom. And this slide shows how we analyze the data recorded with the Alpakita surface array. Please look at the right figure. This figure shows an example of the event display of cosmic ray event, which triggers the surface array of the Alpakita. And these squares shows the positions of the surface detectors. On the other hand, the size of the circle indicates the number of shower particles detected by these detectors, and the color indicates the detection timing. Based on this information, we can reconstruct the energy and the arrival direction of the primary events. For example, for this event, we can estimate the energy approximately about 20 TeV. And also the direction can be reconstructed as the direction as shown with the red arrow. And this slide also shows another other examples of the event display, which demonstrate the detection of cosmic ray events with very high energy. The energies of these events are estimated as over 100 TeV. Okay, from now on, I'm going to present how we calibrate angular resolution of the surface area array of alpha Keta in a data-driven way. It's called even-not method. In this method, first we divide the surface area array into two completely independent subarray, which are shown with blue and red. And then we reconstruct the direction of the same primary event by using these two independent subarrays, and the reconstructed directions are shown with the blue and red arrows. And then taking the opening angle between these reconstructed directions, we can construct a histogram of the opening angle, which is shown in the bottom panel. And the data points are shown with the blue points. On the other hand, our Monte Carlo simulation result is shown with the green histogram. And the median value of the histogram is about 2 degrees for the data, which is well reproduced with our Monte Carlo simulation. And finally, by dividing this median value of the opening angle with 2, then we can give the estimate of the angular resolution of the alpha Keta full array, which is estimated to be about 1 degree. And this result can also be checked from another independent data analysis by observing the moon's shadow of cosmic rays. This figure, left figure, shows the deficit of the cosmic ray events in the direction of the moon with blue colors. And the apparent size and the position of the moon is shown with the yellow circle. We can see that the deficit of cosmic rays, which is the moon's shadow, is successfully observed at 8.0 sigma statistical significance. And we can also see that the cosmic ray moon's shadow is slightly shifted westward by 0.2 degrees from the apparent position of the moon. And this indicates that modal energy of cosmic ray events that trigger our surface area array is about 10 TeV or so. And this is within our expectation. And finally, the right figure shows the cumulative deficit count of cosmic ray events in the moon's direction as a function of the time. And we can see that the result of our data analysis, shown with gray point, is well on the line where we assume the angular resolution of the surface array as 1.0 degrees. So that also validates our result of the angular resolution of about 1 degree for 10 TeV cosmic ray events. And finally, let me present our plan to construct a muon detector for this prototype array. As shown in the right figure, we are going to construct a southwest muon detector. And at the same time, we are going to extend the surface area array to the southwest part to cover the MG to be constructed. And in the next year, we are going to complete the construction of the last 3 muon detectors. And also, we are going to extend the surface area array to the full size of the alpaca array. Okay, then when we complete this construction, then we can expect the detection of many gamma ray sources in 1 year observation. The left figure shows the sensitivity curve of the alpha Keta plus muon detector and alpaca with the 1 year observations. These sensitivity curves are overlaid on the energy spectrum of gamma ray sources within the field of view, and the dotted line is the extrapolation from the lower energy range. And we can see that after the construction of the southwest MD, we can expect the detection of about 5 gamma ray sources with the 1 year observation of alpha Keta. And also, when we completed construction of alpaca, then we can expect the detection of several tens of sources, gamma ray sources, including newly detected sources. And also, you'll be interested in the capability of alpaca of detecting diffuse gamma rays from the galactic center region. And please look at the right figure. This figure compares the sensitivity curve of alpaca with the diffuse gamma rays from the galactic center region observed by HESS. And from this figure, we can see that Alpaca is capable of detecting South PV gamma rays from the galactic center in its more or less 1 year observation. Okay, finally, let me briefly, very simply present our future project called Mega Alpaca. This is our future plan recognized in the Cosmic Ray Committee as presented in the reporter's talk in the last year's International Cosmic Ray Conference. And this project will have the gigantic surface area array with a geometrical area of 1 square kilometers. And also it will have underground muon detector with more than 50,000 square meters to perform the observation sensitive to gamma rays. Actually, if we put the sensitivity curve, estimated sensitivity curve of this Mega Alpaca, then we can see that gamma rays, almost all the gamma non-TV gamma ray sources within our field of view will be detected within the several years of observation with Mega Alpaca. And if you, okay, thank you very much. If you are interested in the details of this future project, please refer to the proceedings of the last year's conference. Okay, let me summarize this talk. My take-home message is we are going to construct MD to the prototype Alpha Kita this year, and we are going to start gamma observation this year. And the next year, we are going to complete the full experiment and going to start the world first South PV gamma observation in the Southern Hemisphere. Thank you very much.
Yeah. Thank you for keeping on time. Questions for Kato Sei? There is one question here.
Hi, Kato Sei. It's Ion Viana from University of São Paulo here. It's just it's a curiosity. What is the cost of this instrument, the Alpaca, and do you have an estimate for the Mega Alpaca, and what would be the cost of this instrument?
Yes, thank you very much for your question. Our experiment is very, very cost effective. And actually, the total cost for the Alpaca, full Alpaca, would be about, currently it will be the $3 million. I think so, $3 million. And also, when we consider the Mega Alpaca, we have to have much cost on the construction of the muon detector, and the size would be from 3,600 to, yes, size will be about 20 times much than Alpaca case. In that case, the cost would increase by 20 times.
Okay, thank you. One more question. Yes.
Okay.
So I was wondering about how the direction is estimated using only the time delay from the observation, because when we have the observed flux in AICT, we do the analysis of the same semi-axis and the eccentricity of the observed flux. And in this case, with only the time delay, you're able to reconstruct your, in this plot.
Yes, exactly. We have two information. One is the number of particles detected, and the other is the detection timing. And by using these two information, we are going to reconstruct the direction. So these two parameters only.
Okay, thank you.
Thank you. Thank you very much, Kato Sei.
Thank you very much.
We have one last talk by our chair, Ulises Varese de Almeida. So it's 2 minutes to the start of the ending ceremony, so I'm not going to keep you listening to a wrap-up talk. You have seen all the presentations. So I would just like then to thank everybody for having participated in this, both the speakers and the people who follow the event. The purpose of this
focus meeting was to bring into the IAU some awareness and try to make some connections with the other fields of more traditional astronomy. I hope that those who have attended have gained some insights on the kind of science that we can do, on the kind of instruments that we operate, and that this be an initial point of contact for future cooperation. I think that as Roberta showed very well in her talk as well, and Hasmik in the beginning, the field is going through a big transformation. So some things, okay, the field is going through a big transformation with new facilities coming up. CTA is going to be really transformational. And also LASSO has broken through many new discoveries, and we expect that SWJO is going to do the same. I think that one characteristic of our field that keeps other wavelengths of astronomy away is the fact that we tend to operate very closed in collaborations where data is proprietary and is difficult to access. But CTA is going to be an open observatory, and in SWJO, we are really looking very hard into making it as open as possible in terms of data access. So I think that if this field also invests in that direction, all the synergies that we have mentioned in interaction with other fields will improve. I think we have demonstrated that we are relevant for many fields of astronomy. So thank you very much. I hope that we can meet again in other IAUs, and that you have had a good time. Thank you very much. Bye-bye.